You are not the center of the universe, but you are the middle, exactly halfway between the smallest thing we can measure and the edge of everything we can see. A quark, one of the fundamental building blocks of matter, sits 10,000 times smaller than the proton in your body. The observable universe stretches 93 billion light-years across empty space, and the distance between those two extremes passes directly through you. That is not poetry, that is mathematics. And the implications are about to get very strange, because scale is not just about big and small. Scale is about what happens when you try to comprehend both at once. When you attempt to hold the entire spectrum of existence in your mind, from the quantum foam where particles blink in and out of reality, to the cosmic web where 100,000 galaxies drift toward an invisible point in space called the Great Attractor. Somewhere in that journey, something breaks. Not the universe, you, your intuition, your sense of proportion, the part of your brain that thinks it understands what words like distance and size actually mean. This video is going to walk you through every meaningful scale of existence. From particles that exist at dimensions so small we have to invent new kinds of numbers just to write them down, all the way to structures so vast they take light itself 500 million years to cross. We are going to visit the Laniakea Supercluster. We are going to stand at the edge of cosmic voids where nothing exists for hundreds of millions of light years in any direction. And by the time we reach the end, you will understand why the observable universe is not the whole universe, why 93 billion light years is just the beginning, and why the question of where you fit in all of this is far more complicated than anyone told you. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. We need to start somewhere. That's harder than it sounds, because when you try to find the bottom of reality, the point where you can't go any smaller, the universe stops cooperating. It stops making sense in any way your brain is wired to handle, and it keeps going down, further than you think, into scales so small that calling them tiny is like calling the sun warm, inadequate to the point of comedy. So let's try anyway. Picture a grain of sand. Fine. Now imagine cutting it in half, then in half again. Keep going. Cut through the silicon dioxide crystal structure. Slice past the molecules, carve through the atoms themselves, peel apart the nucleus, separate the protons and neutrons. And then, if you're still cutting, if you haven't given up or gone insane, you'll hit something that refuses to be divided any further. You'll hit a quark. Quarks are, as far as we can currently tell, the smallest building blocks of matter. They are fundamental particles, meaning they have no internal structure. You can't break them into smaller pieces, because there are no smaller pieces. A quark is not made of anything, it just is. How small are we talking? The best measurements we have put a quark at, roughly 10 to the power of -19 meters across. That's a decimal point followed by 18 zeros and then a 1. To put that in perspective, if you scaled a quark up to the size of a marble, a hydrogen atom, the thing that quark lives inside would be about the size of Earth. And if you kept that same scaling ratio and blew Earth up to match, the solar system would stretch across multiple galaxies. That is the bottom, or at least that's as close to the bottom as particle accelerators and quantum field theory can currently take us. Nobody has ever seen a quark by itself. You can't. They don't exist in isolation. Try to pull one out of a proton, and the energy you pump in just creates more quarks. It's like trying to cut a magnet in half to isolate a north pole. You just get two smaller magnets. The universe has rules about this, and the universe does not negotiate. Quarks come in 6 types, which physicists call flavors, because apparently when you spend enough time thinking about particles smaller than the wavelength of visible light, you start naming things like a dessert menu. The flavors are up, down, charm, strange, top and bottom. Every proton in your body is made of 2 up quarks and 1 down quark. Every neutron is 2 down and 1 up. That's it. That's the recipe for the nucleus of every atom in existence. 3 quarks, held together by particles called gluons, which are themselves a whole other nightmare we'll get to in a moment. The rules governing quarks are described by something called quantum chromodynamics, a branch of physics so mathematically dense that even physicists who work in the field will admit it makes their heads hurt. The short version is that quarks carry a property called color charge, not actual color. There is no red quark sitting next to a blue quark like toy blocks. Color charge is just a name for a type of force that only quarks experience. It's the strong nuclear force, and it is strong. It's the reason atomic nuclei hold together despite being packed with positively charged protons that should, by all rights, be repelling each other into oblivion. Gluons are the particles that carry that force. They glue quarks together, hence the name. And here's where it gets strange. Gluons themselves carry color charge. That means they interact not just with quarks, but with each other. Photons, the particles of light, don't do that. Photons don't interact with other photons under normal circumstances. They just pass through each other. Gluons don't. Gluons grab onto gluons. The strong force gets stronger the further apart you try to pull quarks. It's like a rubber band that never snaps. Pull hard enough and the band just spawns a new quark-antiquark pair out of the vacuum. The universe would rather create matter than let you see a quark by itself. Quarks are not the only fundamental particles, by the way. There's a whole zoo of them. Electrons, for instance. You've heard of electrons. They orbit atomic nuclei. They flow through wires. They are the reason your phone works and the reason lightning exists. An electron is about 2,000 times lighter than a proton, and unlike a proton, it's truly fundamental. You can't crack it open. There's nothing inside. It's a point particle, meaning it has no measurable size at all. Technically, according to quantum field theory, it's a localized excitation in the electron field, but that's not a sentence that helps anyone sleep at night. Then there are neutrinos. Neutrinos are ghosts. They have almost no mass. They don't interact with electromagnetic fields, which means they don't bounce off anything. Right now, billions of neutrinos are passing through your body every second. Most of them were born in the nuclear furnace at the core of the sun. They zip through the sun's outer layers, through the 93 million miles of empty space between the sun and Earth, through the atmosphere, through the roof over your head, through your skull, through your brain, and out the other side without slowing down or noticing you existed. To a neutrino, solid matter is basically a suggestion. Physicists detect neutrinos by building enormous tanks of ultra-pure water deep underground and waiting for the 1 in a trillion chance that a neutrino will actually collide with a nucleus and produce a tiny flash of light. That's the level of effort required to prove these things are real. And then there are the bosons. Photons are bosons, so are gluons. So are the W and Z bosons, which carry the weak nuclear force, the force responsible for certain types of radioactive decay. And then there's the Higgs boson, discovered in 2012 at the Large Hadron Collider, after a search that lasted decades and cost billions of dollars. The Higgs is special because it's tied to the Higgs field, a field that permeates all of space and gives other particles their mass. Without the Higgs field, electrons and quarks would be massless and would zip around at the speed of light. Matter as we know it wouldn't exist. Stars wouldn't form. Atoms wouldn't bind. You wouldn't be here. The Higgs boson is the ripple in that field. Finding it was one of the great triumphs of experimental physics, and also one of the most terrifying. Because the mass of the Higgs boson, about 125 times the mass of a proton, sits in a range that makes the universe look unstable. According to some calculations, the Higgs field might not be in its lowest energy state. It might be sitting in what's called a false vacuum, a temporary valley that could, given the right nudge, collapse into a deeper true vacuum. If that happened, a bubble of true vacuum would expand outward at the speed of light, rewriting the laws of physics as it went. Everything inside the bubble, every atom, every bond, every structure would cease to exist in its current form. The good news is that if it happens, you won't see it coming. The bad news is that it's technically possible, and we have no way to stop it. Welcome to the quantum realm. It only gets weirder from here. At scales this small, the concept of size starts to break down. You can't measure the position of a particle the way you measure the length of a table. Particles don't have definite positions until you observe them. Before that, they exist in a state called superposition, a kind of probabilistic smear across all the places they could be. Schrödinger's cat is the famous thought experiment. A cat in a box with a vial of poison that may or may not have been released, depending on whether a radioactive atom has decayed. Until you open the box, the cat is both alive and dead. That sounds like philosophy. It's not. It's math. And the math says the particle is genuinely in multiple states at once until something forces it to pick one. This isn't a limit of our instruments. It's not that the particle has a real position and we just don't know it yet. The particle does not have a position, it has a wave function, a mathematical description of all possible positions weighted by probability. Measure it, and the wave function collapses. The particle picks a spot, but before you measured, it was everywhere and nowhere, and that is not a metaphor. Then there's entanglement. Take two particles, let them interact, then separate them by any distance you want, a mile, a light year, it doesn't matter. Measure one, and you instantly know something about the other, no matter how far apart they are. Einstein called this spooky action at a distance and hated it. He thought it meant quantum mechanics was incomplete, that there had to be hidden variables we weren't seeing. He was wrong. Experiments have tested this over and over. Entanglement is real. Measure the spin of one particle, and the spin of its entangled partner is immediately determined, faster than any signal could have traveled between them. This does not allow faster than light communication, by the way. The results of your measurement are random. You can't control what you get, so you can't encode a message. But the correlation is there, instant and absolute across any distance. The universe does not care about your intuition. It does not care that this feels impossible. And then there's wave-particle duality. Light behaves like a wave. It has frequency, wavelength, interference patterns. Shine light through two slits, and it creates a pattern of bright and dark bands on a screen, the hallmark of waves overlapping and cancelling each other out. But light also behaves like a particle. Hit a metal surface with light, and you can knock electrons loose, one photon at a time. Einstein won his Nobel Prize for explaining that, not for relativity, for the photoelectric effect. Electrons do the same thing. Fire them one at a time through a double slit and they still create an interference pattern, as if each electron is somehow passing through both slits and interfering with itself. But if you try to measure which slit the electron actually goes through, the interference pattern disappears. The electron stops acting like a wave and starts acting like a particle. The act of measurement changes the outcome. Not because you bumped it, because the universe does not commit to a reality until something forces it to. This is not a glitch. This is how the universe works at small scales. It is deeply, fundamentally, uncomfortably weird, and it has been verified in experiment after experiment for more than a century. Quantum mechanics is the most successful scientific theory ever devised. It predicts the behavior of particles with absurd precision, and nobody knows why it works. We have the math. We can calculate probabilities and energy levels and decay rates to 15 decimal places. But the why, the mechanism underneath that makes particles behave this way, remains completely mysterious, and we haven't even hit the bottom yet. There is a length scale called the Planck length. It sits at about 10 to the power of negative 35 meters. That is 20 million trillion times smaller than a quark. At that scale, the fabric of space-time itself is thought to break down into something called quantum foam, a seething froth of virtual particles popping in and out of existence, space-time itself fluctuating like the surface of a boiling pot. Time and space stop being smooth. They become grainy, pixelated, uncertain. We have no instruments that can probe the Planck scale. We likely never will. The energy required to study something that's small would be so concentrated that it would collapse into a black hole before you could measure it. The Planck length is not just small, it's the length scale at which general relativity and quantum mechanics, the two pillars of modern physics, start screaming at each other. Relativity describes gravity as the curvature of space-time. Quantum mechanics describes everything else as particles and fields. At the Planck scale, both are needed, and they don't fit together. Every attempt to merge them produces infinities and nonsense. This is the frontier. This is where we run out of road. Below the Planck length, the equations stop working. The concept of distance becomes meaningless. The idea of measuring anything smaller doesn't just become impractical, it becomes undefined. You can't have a ruler shorter than the Planck length because the ruler itself would warp spacetime so much that the measurement would destroy what you're trying to measure. So that's the bottom. Quarks, leptons, bosons, fields, and then a threshold beyond which the universe stops answering questions. You are made of this. Every atom in your body is built from particles that exist in superposition until something observes them that are entangled with other particles across distances that should make correlation impossible, that behave like waves and particles depending on what you're looking for. You are a standing wave in a quantum field, a temporary pattern of energy that has somehow become stable enough to think about itself. And here's the thing. This isn't the weird part, this is just the foundation, the normal part, the part where the rules are at least written down, even if they don't make sense, because now we have to build upward. We have to take these impossible particles that refuse to behave and assemble them into atoms, atoms into molecules, molecules into cells, cells into you, quarks into stars, stars into galaxies, galaxies into clusters, clusters into the cosmic web. And somewhere along that climb, across 45 orders of magnitude, the weirdness of the quantum realm gives way to the apparent solidity of the everyday world. Particles that exist in probabilistic clouds somehow lock together into objects you can hold, tables you can sit at, planets you can stand on. The question isn't just how big the universe is, the question is how it manages to be anything at all. How does a cosmos built on uncertainty produce certainty? How does a foundation made of ghosts hold up mountains? The answer starts one level up, at the scale where quantum strangeness begins to crystallize into something recognizable, where particles stop being probabilities and start being things, where the electron clouds collapse into atoms and atoms stack into matter, and matter builds the world you've spent your entire life assuming was solid. That's the next step. That's where we're going. From quarks to atoms. From the quantum to the tangible. From the smallest things we know to the first things you can see. So you've made it through the quantum basement. You've seen the particles that refuse to sit still, the forces that make no intuitive sense, and the scales where reality itself becomes negotiable. Now comes the harder part. Not harder because the physics is more complicated. Harder because you have to explain how any of that chaos manages to calm down long enough to build something you can touch. This is where the universe pulls off its most impressive trick. It takes the probabilistic madness of quarks and electrons, particles that only exist in definite states when something bothers to look at them, and it stacks them into atoms, atoms into molecules, molecules into cells, cells into you. Somewhere between the Planck length and the length of your hand, the universe crosses a threshold. It goes from deeply weird to apparently solid, and nobody has a clean answer for why that transition happens or where exactly the line is. Let's start with the atom. You've heard the name. You probably learned in school that atoms are the building blocks of matter. That's true, but it's also misleading in the same way calling a skyscraper a stack of bricks is true. Technically accurate, but it misses the entire engineering problem. An atom is not a thing in the way a marble is a thing. It doesn't have a hard surface. It doesn't have edges. If you tried to grab one, there would be nothing to grab. What we call an atom is actually a cloud of probability wrapped around a core so small that it barely registers as real. Here's the structure. At the center sits the nucleus, a cluster of protons and neutrons held together by the strong nuclear force. Protons are positively charged, neutrons have no charge. Together they account for more than 99.9% of the atom's mass. The nucleus of a hydrogen atom, the simplest atom in existence, is just a single proton. The nucleus of a carbon atom has 6 protons and usually 6 neutrons. Uranium has 92 protons and typically 146 neutrons. The bigger the nucleus, the heavier the atom. The size of a nucleus is roughly 1 femtometer across. That's 10 to the power of -15 meters, 1 quadrillionth of a meter. If you scaled a proton up to the size of a marble, the nucleus of a heavy atom like gold would be about the size of a grapefruit. Still small, but at least measurable in familiar terms. Now here's where it gets strange. The atom itself is about 10,000 times larger than the nucleus. The actual number varies depending on the element, but a typical atom has a diameter of around 1 angstrom, which is 10 to the power of -10 meters, 1/10 billionth of a meter. That's 10,000 times bigger than the nucleus sitting at its center. So where's the rest of the atom? What fills that space? Nothing. And also electrons. Electrons orbit the nucleus, except orbit is the wrong word because it implies a definite path, like a planet around a sun. Electrons don't do that. They exist in regions of space called orbitals, which are essentially probability clouds. The electron is not at a specific point. It's smeared across a volume of space where it's likely to be found if you bother to measure it. The orbital is the shape of that smear. Different orbitals have different shapes. Some are spheres, some are dumbbells, some look like cloverleafs. The shapes are determined by the quantum numbers that describe the electron's energy, angular momentum, and spin. And yes, spin is another term that doesn't mean what it sounds like. An electron doesn't spin the way a top spins. Spin is an intrinsic property, a kind of angular momentum that has no classical analog. Trying to visualize it will hurt your brain, and physicists gave up trying decades ago. The key point is this. The part of the atom that takes up space, the part that prevents your hand from passing through the table, is not solid. It's an electron cloud. And the nucleus, the part with all the mass, occupies a volume so small that if you removed all the empty space from every atom in your body, the remaining matter would fit inside a grain of sand. You are mostly nothing. The table is mostly nothing. The floor, the walls, the planet beneath your feet, all of it is mostly nothing held together by forces that operate at distances far larger than the objects generating them. Atoms stay atoms because of a balance. The positively charged nucleus attracts the negatively charged electrons. The electrons want to fall in, but quantum mechanics won't let them. The Heisenberg uncertainty principle says you can't know both the position and momentum of a particle with perfect precision. Trap an electron too close to the nucleus, and its position becomes well defined, which means its momentum becomes wildly uncertain. The electron's energy spikes. It pushes back. The result is a stable orbit, or more accurately, a stable probability distribution. The electron doesn't fall into the nucleus because the rules of quantum mechanics create an effective repulsion that counterbalances the electromagnetic attraction. This is not a force in the traditional sense, it's a quantum pressure, and it's the reason matter has volume. If electrons could collapse into the nucleus, atoms would shrink to the size of nuclei, and everything would compress into a dense soup of neutrons. The fact that you can't walk through walls is a direct consequence of the Pauli exclusion principle and the uncertainty principle acting together to keep electrons from occupying the same space. Atoms don't just sit around by themselves, they bond. They link up into molecules, and that's where chemistry starts. There are different types of bonds. The simplest is the ionic bond, where one atom donates an electron to another. Sodium, for instance, has one loosely held electron in its outermost shell. Chlorine is one electron short of a full shell. Sodium hands over the electron. Sodium becomes positively charged. Chlorine becomes negatively charged. Opposite charges attract. The two atoms stick together. You get sodium chloride, table salt. Covalent bonds are more interesting. In a covalent bond, atoms share electrons. The electrons don't belong to one atom or the other. They occupy molecular orbitals that span both nuclei. The shared electrons spend time between the atoms, and the attraction between the negatively charged electron cloud and the positively charged nuclei holds the molecule together. Water is a covalent molecule. One oxygen atom bonds with two hydrogen atoms. Oxygen has 6 electrons in its outer shell and wants 8. Each hydrogen has 1 electron and wants 2. Share electrons and everyone gets what they want. The result is H2O, and the shape matters. The molecule is bent, not linear, because the electron pairs around the oxygen atom repel each other and force the hydrogens into a specific angle. That bend gives water a polarity. One side of the molecule is slightly positive, the other slightly negative. That polarity is why water is such a good solvent. It's why ice floats. It's why life as we know it can exist. Molecules can get vastly more complex than water. DNA is a molecule, so is hemoglobin. So is the protein folding inside your cells right now to carry out the chemical reactions that keep you alive. Some biological molecules contain thousands of atoms arranged in precise three-dimensional structures. A single wrong atom in the wrong place and the molecule doesn't work. Enzymes are molecular machines. They grab other molecules, twist them, break specific bonds, and release the products. They do this billions of times per second with almost no errors. None of this is designed. None of it required a blueprint. Molecules arrange themselves into these shapes because that's the configuration with the lowest energy given the electromagnetic forces at play. Chemistry is physics on autopilot. The same rules that describe how electrons behave around a single nucleus also describe how they behave around 10,000 nuclei linked into a protein. The math gets harder, but the principles don't change. Molecules stack into structures, structures stack into cells, Cells are where matter stops being chemistry and starts being biology. The dividing line is blurry, but it's somewhere around the point where a system can maintain itself, reproduce, and respond to its environment. A typical human cell is about 10 micrometers across. That's 10 millionths of a meter. A red blood cell is smaller, closer to 7 micrometers. A neuron can be a meter long if you count the axon, but the cell body itself is still in the micrometer range. Bacteria are smaller still. Escherichia coli, the bacterium that lives in your gut and shows up in every biology textbook, is about 2 micrometers long and 1 micrometer wide. Viruses are smaller than bacteria, but they're not technically alive. They can't reproduce on their own. They're just protein shells carrying genetic instructions, hijacking cells to make copies of themselves. Inside a cell, the complexity is staggering. There's a membrane holding everything together, made of lipids arranged in a double layer. Proteins are embedded in that membrane, acting as gates and pumps and receptors. Inside the membrane is the cytoplasm, a gel-like substance full of dissolved molecules, ions and structures called organelles. The nucleus, not to be confused with the atomic nucleus, contains the cell's DNA. Mitochondria generate energy by breaking down sugars and fats. Ribosomes build proteins by reading messenger RNA and stringing amino acids together in the correct order. The endoplasmic reticulum folds and ships those proteins. The Golgi apparatus packages them for export. This is happening in every cell in your body right now. You have somewhere around 37 trillion cells. Each one is running thousands of simultaneous chemical reactions, coordinated by feedback loops and signaling molecules. The fact that it works at all is astonishing. The fact that it works well enough for you to sit here and think about it is borderline miraculous. The jump from single cells to multicellular organisms is another threshold. Single-celled organisms like bacteria have been around for more than 3.5 billion years. Multicellular life showed up much later, maybe a billion years ago, and it required cells to start cooperating. Specialization happened. Some cells became good at absorbing nutrients. Others became good at moving. Others became good at sensing the environment. Group those specialists together and you get tissues. Group tissues together and you get organs. Group organs together and you get an organism. You are an organism. You are also an ecosystem. The bacteria in your gut outnumber your own cells. They help digest food, produce vitamins, train your immune system. Without them, you would die. You are not a single entity. You are a colony, a walking biome. A temporary alliance of systems that will eventually dissolve back into the environment when your cells stop cooperating and the whole structure falls apart. But while it lasts, you perceive yourself as solid. You feel like a coherent thing. That perception is a trick your brain plays, stitching together sensory data into a model of the world that's useful but not accurate. You don't feel the constant molecular churn. You don't sense the proteins folding in your cells or the ions pumping across membranes. You don't perceive the atoms in your skin vibrating at room temperature or the electrons hopping between energy levels. Your brain filters all of that out and presents you with a clean, simplified version of reality where objects have edges and surfaces, and you can trust that the floor will hold you up. This is the scale where humans live, the scale where quantum weirdness has averaged out into classical predictability, the scale where you can make plans and expect the universe to behave. Here's the perspective check. You are roughly 1.7 meters tall if you're average. Let's call it 2 meters to make the math easier. A meter is a human scale unit. We defined it. Originally, it was 1/10 millionth of the distance from the equator to the North Pole, but now it's defined by the distance light travels in 1,299,792,458 of a second. Either way, it's a length that fits comfortably in human experience. Go smaller and you hit the millimeter. A grain of sand is about a millimeter. A flea is a couple millimeters. The tip of a pin. You can see these things without help, but they're at the edge of visibility. Go smaller still, and you need a magnifying glass. A human hair is about 70 micrometers across. Red blood cells are 7 micrometers. Bacteria are in the low single-digit micrometers. Below that, you need a microscope. Go bigger and you hit the meter. A car is a few meters long. A house is tens of meters. A skyscraper is hundreds of meters. These are still comprehensible. You can walk the distance. You can look at the structure and understand its size relative to your body. Go bigger still and you hit the kilometer. 1,000 meters. A decent walk. You can cover a kilometer in 10 or 15 minutes. The distance feels real because you've traveled it. You've experienced the time it takes to cross that space. Now go bigger. 10 kilometers, 100, 1,000. At some point, the numbers stop meaning anything. You can say the distance from New York to Los Angeles is about 4,000 kilometers, but you don't feel that distance the way you feel a meter. Your brain has no internal reference for it. It's just a number, a label. The experiential connection breaks down, and that's still on Earth. That's still within the scale of a single planet. We haven't even left the ground yet. Here's the uncomfortable truth. The scale you experience as normal, the scale where you can hold objects and walk distances and perceive time passing at a reasonable rate, is a tiny sliver of the full range. You exist in a narrow band between the quantum and the cosmic. Below you, particles behave in ways that make no intuitive sense. Above you, distances stretch so far that light takes years to cross them. You are perched in the middle, on a scale where the rules happen to produce solid objects and predictable motion. And you are only able to think about any of this because evolution shaped a brain that works at this specific scale. If you were the size of a bacterium, the world would look completely different. Water wouldn't be a fluid, it would be a thick syrup. Brownian motion, the random jiggling of molecules, would toss you around like a leaf in a hurricane. Gravity would be irrelevant, surface tension would dominate. A drop of water would be a vast ocean, and you'd never escape it because the stickiness of the surface would hold you like glue. If you were the size of a planet, time would feel different. Continents would drift like clouds. Oceans would slosh in slow motion. A day would pass in what felt like seconds. You'd watch stars evolve, galaxies rotate, the whole cosmic ballet playing out on a timescale that made sense to you. But you're not a bacterium. You're not a planet. You're a 2-meter-tall sack of water and carbon compounds, standing on a rock in space, staring up at the sky and trying to make sense of the numbers. The scale you live at is not special. It's not the center of anything. It's not the natural size for conscious beings. It's just the size where evolution happened to produce something complicated enough to ask the question. And now that the question's been asked, the answer keeps getting bigger. Because here's the thing, the scales we've covered so far, from quarks to cells to humans, span about 25 orders of magnitude. That's a factor of 10 to the power of 25, a 1 with 25 zeros after it. That sounds huge. It is huge, but it's only half the journey. We've climbed from the bottom of the quantum realm to the middle, to the scale where you and I exist, and we're not even close to the top. There's another 20 orders of magnitude waiting above us, 20 orders of magnitude where the rules change again, where gravity starts to matter more than chemistry, where distances are measured in light years instead of meters, where the objects we're talking about are no longer molecules or cells or people, they're stars, planets, galaxies, structures so large that they bend space-time itself, so old that the light reaching us now started its journey before Earth existed. You are made of atoms. Atoms are made of quarks and electrons. Quarks and electrons are excitations in quantum fields. Fields permeate space. Space is expanding. Expansion is accelerating. And somewhere in that chain of facts, your body transitions from a quantum system to a classical object, to a speck of dust floating in an ocean of emptiness so vast that the human mind has no machinery to process it. But we're going to try anyway. Because the next step up isn't just about bigger numbers. It's about the fact that everything you're made of, every atom in your body, was forged inside a star that died before the sun was born. You're not just standing on a planet, you're standing on a fragment of exploded stars. And those stars are not scattered randomly, they're organized into galaxies. And those galaxies are not scattered randomly either. They're threaded into a web that stretches across the entire observable universe, a structure so large that light takes billions of years to cross it. That's where we're going next, not to the everyday world, but to the place the everyday world came from, to the furnaces where atoms are born and the gravitational wells where planets coalesce, to the solar system, to the stars, to the thing that made you possible in the first place. You live on a rock. That's not meant to be poetic or reductive. It's just the clearest description of what Earth actually is. A ball of mostly iron and silicon, about 12,700 kilometers across, wrapped in a thin film of water and gas, spinning through space at roughly 30 kilometers per second. You don't feel the motion because everything around you is moving at the same speed. The air, the ground, the coffee cup on your desk, all of it locked into the same orbit around a medium-sized star we call the Sun. The Sun sits at the center of our solar system, and before we go any further, we need to recalibrate what the word system actually means. Because when most people think of the solar system, they picture a diagram from a textbook. 8 planets arranged in neat concentric circles around a bright yellow dot. Maybe an asteroid belt sketched in between Mars and Jupiter. Maybe a few labels, distances compressed so everything fits on a single page. That diagram is a lie, not because the information is wrong, but because the scale is so distorted that it makes the solar system look cozy, manageable. The kind of neighborhood you could walk across if you had a few hours. You could not. The solar system is enormous, unimaginably, stupidly enormous. And the distances between objects are so large that even light, the fastest thing in the universe, takes hours to cross from one side to the other. Let's start with Earth. You're standing on it right now, so it's a good reference point. Earth has a diameter of about 12,700 kilometers. That's big enough that you can't see the curvature from ground level. You have to get high, really high. Airplanes fly at about 10 kilometers up, and from that altitude, the horizon still looks flat. You don't start to see the curve until you're at least 50 kilometers above the surface, and even then it's subtle. Astronauts on the International Space Station orbit at about 400 kilometers, and from there, Earth looks like a sphere, a big one. The kind you can stare at for hours and still not take in all the detail. Now imagine you're standing on Earth's surface, looking up at the moon. The moon is about 384,000 kilometers away. That sounds like a lot, and it is. Light takes about 1.3 seconds to travel from Earth to the moon. During the Apollo missions, there was a noticeable delay in radio communications between mission control in Houston and the astronauts on the lunar surface. You'd ask a question, wait, and then hear the answer. The delay wasn't because the equipment was slow. It was because the signal had to cross 384,000 kilometers twice, once out and once back. That's how far away the moon is. Close enough to see with your naked eye, but far enough that light needs more than a second to get there. The moon is the closest major object to Earth. Nothing else comes close. And already we're talking about distances where human intuition starts to fail. Now let's talk about the Sun. The Sun is about 150 million kilometers from Earth. We call that distance 1 astronomical unit, or AU, and it's the baseline for measuring everything else in the solar system. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. That means when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. If the Sun suddenly vanished, blinked out of existence like a light bulb, you wouldn't know for 8 minutes. For those 8 minutes, the sky would still be bright. Earth would still be in orbit. And then, all at once, the light would go out and the planet would start drifting into the dark. The Sun is not small, it's huge. Its diameter is about 1.4 million kilometers. You could line up 109 Earths across the Sun's equator. You could fit about 1.3 million Earths inside its volume. The Sun contains 99.8% of all the mass in the solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust, adds up to a rounding error. The Sun is the solar system. Everything else is debris. Mercury orbits closest to the Sun at about 0.4 AU. That's roughly 58 million kilometers. It's a scorched, cratered ball of rock with no atmosphere and surface temperatures that swing from 430 degrees Celsius on the day side to minus 180 degrees at night. Light from the Sun reaches Mercury in about 3 minutes. Venus is next at 0.7 AU, about 108 million kilometers. It's roughly the same size as Earth, but the similarities end there. Venus has a thick carbon dioxide atmosphere that traps heat so effectively that the surface temperature sits around 470 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is about 90 times what you experience at sea level on Earth. Standing on Venus would feel like being a kilometer underwater, except everything is on fire. Light from the Sun takes about 6 minutes to get there. Earth is third, 1 AU, you know this one. Mars is fourth, at about 1.5 AU, roughly 228 million kilometers. It's smaller than Earth, about half the diameter, and it has a thin atmosphere that's mostly carbon dioxide. The surface is cold, averaging around minus 60 degrees Celsius, and it's covered in iron oxide dust that gives the planet its red color. Light from the Sun takes about 12 minutes to reach Mars. Between Mars and Jupiter sits the asteroid belt, a region filled with rocky debris left over from the solar system's formation. The largest object in the belt is Ceres, a dwarf planet about 950 kilometers across. Most asteroids are much smaller. The belt stretches from about 2 AU to roughly 3.2 AU. It's not dense. If you flew a spacecraft through the asteroid belt, you probably wouldn't see anything. The asteroids are spread out over such a huge volume of space that the average distance between them is hundreds of thousands of kilometers. Hollywood has lied to you. There's no dodging and weaving through a crowded field of tumbling rocks. There's just emptiness with the occasional pebble drifting by. Jupiter is the giant. It sits at about 5.2 AU, roughly 778 million kilometers from the Sun. Light takes about 43 minutes to get there. Jupiter is enormous. Its diameter is about 143,000 kilometers. You could fit more than 11 Earths side by side across Jupiter's equator. You could fit about 1,300 Earths inside its volume. It's a gas giant, meaning it doesn't have a solid surface. The atmosphere just gets thicker and hotter as you descend until eventually the pressure is so high that hydrogen stops behaving like a gas and starts behaving like a liquid metal. Jupiter has at least 79 moons, including Ganymede, the largest moon in the solar system, and Europa, which we've already established is hiding an ocean. Saturn is next, at 9.5 AU, about 1.4 billion kilometers from the Sun. Light takes about an hour and 20 minutes to reach Saturn. It's slightly smaller than Jupiter, but it's still massive. Its diameter is about 120,000 kilometers, and it's famous for its rings. The rings are made of ice particles and rock fragments ranging in size from dust grains to boulders. They're thin, only about 10 meters thick in most places, but they stretch out for hundreds of thousands of kilometers. Saturn has at least 82 moons. Titan, the largest, has a thick nitrogen atmosphere and lakes of liquid methane on its surface. Uranus sits at 19.2 AU, about 2.9 billion kilometers. Light takes 2 hours and 40 minutes to get there. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth. Its diameter is about 51,000 kilometers. It's tilted on its side, rotating at an angle of about 98 degrees relative to its orbit. Nobody knows why. The leading theory is that something big hit it early in the solar system's history and knocked it over. Neptune is the farthest planet, at 30 AU, about 4.5 billion kilometers from the Sun. Light takes about 4 hours to reach Neptune. It's slightly smaller than Uranus, with a diameter of about 49,000 kilometers. It's blue, colored by methane in its atmosphere, and it has the fastest winds in the solar system. Storms on Neptune can reach speeds of over 2,000 kilometers per hour. That's where most diagrams stop. 8 planets, Sun in the middle, everything contained within a tidy 30 AU bubble. But that's not where the solar system ends, not even close. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets that stretches from about 30 AU to roughly 50 AU. Pluto lives here. Pluto is about 2,370 kilometers across, smaller than Earth's moon, and its orbit is tilted and elliptical. It's not alone. There are thousands of objects in the Kuiper Belt, chunks of ice and rock left over from when the solar system formed. Some are large enough to be considered dwarf planets. Eris, Haumea, Makemake, names borrowed from mythology to label frozen rocks billions of kilometers away that no human will ever visit. Light from the Sun takes about 6 hours to reach the inner edge of the Kuiper Belt and more than 8 hours to reach the outer edge. When the New Horizons spacecraft flew past Pluto in 2015, the radio signal carrying the images and data back to Earth took 4.5 hours to arrive. Scientists on the ground had to wait 4.5 hours after the flyby to see the first pictures. That's how far away Pluto is, and we're still not done. Beyond the Kuiper Belt lies the Oort cloud, a theoretical shell of icy bodies that surrounds the entire solar system. Nobody has ever seen the Oort cloud. We infer its existence from the comets that occasionally fall inward toward the Sun, their orbits suggesting they came from a distant reservoir far beyond the planets. The Oort cloud is thought to extend from about 2,000 AU to as far as 100,000 AU from the Sun. That's roughly 1.6 light years. A light year, not light hours, not light days. An entire year's worth of distance traveled by light. The Sun's light takes more than a year to reach the outer edge of the Oort cloud. At that distance, the Sun would no longer look like a disk. It would look like a bright star. Bright enough to cast shadows maybe, but just barely. The solar wind, the stream of charged particles flowing outward from the sun, would be so thin and weak that it would effectively stop. The boundary where the solar wind loses its push and interstellar space begins is called the heliopause. Voyager 1, the most distant human-made object, crossed the heliopause in 2012 at a distance of about 121 AU. It's still out there, still sending back data, though the signal is so faint that NASA has to use massive dish antennas just to pick it up. The Oort cloud defines the gravitational boundary of the solar system. Objects out there are still loosely bound to the sun, but only barely. A passing star could nudge them. A gravitational wave from a distant event could jostle them. Some of them will eventually fall inward and become comets. Others will drift away entirely, lost to interstellar space. So here's the scale. The solar system, defined by the Oort cloud, is about 2 light-years across. Earth sits 1 AU from the Sun, which is 8 light-minutes. The gap between those two numbers is staggering. If you built a scale model where Earth was the size of a marble, the Sun would be about 1.5 meters across and about 150 meters away. Neptune would be 4.5 kilometers away. The inner edge of the Oort cloud would be 320 kilometers away, and the outer edge would be 16,000 kilometers away, roughly the diameter of the actual Earth. You can't fit that on a page. You can barely fit it in your head. Now let's leave the solar system. Let's talk about the nearest stars. The closest star to the Sun is Proxima Centauri, a small red dwarf sitting about 4.2 light-years away. Light from Proxima Centauri takes 4.2 years to reach us. That means when you look at Proxima Centauri through a telescope, you're seeing it as it was 4 years ago. If something dramatic happened there, an explosion, a planetary collision, anything, you wouldn't know about it for more than 4 years. 4.2 light-years translates to about 268,000 AU. That's roughly 268,000 times the distance from Earth to the Sun. If you tried to drive to Proxima Centauri at highway speeds, it would take you about 45 million years. If you flew there on the fastest spacecraft humanity has ever built, Voyager 1, it would take about 73,000 years. We're not going there, not anytime soon. Proxima Centauri is part of a triple star system called Alpha Centauri. The other 2 stars, Alpha Centauri A and Alpha Centauri B, are both larger and brighter than Proxima, and they orbit each other in a slow gravitational dance. Proxima orbits the pair at a much greater distance, bound to them by gravity but only loosely. The system as a whole is the closest group of stars to our Sun, and even then, the gap is enormous. Beyond Alpha Centauri, the nearest stars are scattered across distances of 5, 10, 15 light-years. Barnard's star is about 6 light-years away. Wolf 359 is about 7.9 light-years. Sirius, the brightest star in our night sky, is about 8.6 light-years away. These are our neighbors, the closest things to us that are not part of our solar system, and they're all unimaginably far away. Stars are not evenly distributed. The space between them is vast. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, and the average distance between stars in our region of the galaxy is about 5 light-years. 5 light-years of mostly nothing. No planets, no asteroids, no comets. Just a thin haze of hydrogen gas and dust, so diffuse that it's effectively a vacuum. Interstellar space is empty in a way that's hard to overstate. You could travel for years without passing anything larger than a grain of sand. Stars themselves are the reason you're here. Every atom in your body heavier than hydrogen was forged inside a star. Carbon, oxygen, nitrogen, calcium, iron. All of it came from stellar fusion or from the explosive deaths of massive stars. Stars are furnaces. They take hydrogen, the simplest and most abundant element in the universe, and squeeze it under immense pressure and heat until the nuclei fuse together to form helium. That fusion releases energy, a lot of energy, enough to make a star shine for billions of years. Our Sun is a main sequence star, meaning it's in the stable phase of its life, where it fuses hydrogen into helium in its core. It's been doing this for about 4.6 billion years, and it will keep doing it for another 5 billion or so. When the hydrogen in the core finally runs out, the Sun will start fusing helium into heavier elements. It will swell into a red giant, large enough to engulf Mercury and Venus, and possibly Earth. Eventually, the outer layers will drift away, leaving behind a hot, dense core called a white dwarf. That white dwarf will cool slowly over trillions of years until it becomes a cold, dark lump of carbon and oxygen drifting through space. That's the fate of a star like the Sun. Larger stars have more dramatic endings. Stars more than about 8 times the mass of the Sun fuse heavier and heavier elements in their cores, building up layers like an onion. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, silicon into iron, and then it stops. Iron doesn't release energy when it fuses, it absorbs energy. The core of the star collapses in a fraction of a second, and the rebound sends a shockwave tearing through the star's outer layers. The star explodes, a supernova. Supernovae are among the most energetic events in the universe. For a brief period, a single exploding star can outshine an entire galaxy. The explosion scatters the heavy elements forged in the star's core across space, seeding the surrounding gas with carbon, oxygen, silicon, iron, and every other element heavier than helium. Those elements eventually become part of new stars, new planets, new life. You are made of supernova debris. Every breath you take, every thought you think, every cell in your body is built from atoms that were forged in the cores of dying stars billions of years ago. The Sun is not special. It's one of hundreds of billions of stars in the Milky Way. Most of those stars are smaller and dimmer than the Sun. Red dwarfs, stars with less than half the Sun's mass, make up about 70% of all stars in the galaxy. They burn their fuel slowly and can live for trillions of years. Some red dwarfs that formed in the early universe are still on the main sequence today, barely changed since they ignited. A smaller fraction of stars are larger and brighter than the Sun. Blue giants, stars with 10 or 20 times the Sun's mass, burn through their fuel in just a few million years. They're rare, but when they die, they go out spectacularly. Some leave behind neutron stars, objects so dense that a teaspoon of their matter would weigh 1 billion tons. Others collapse completely, forming black holes. The life cycle of stars is the engine of cosmic chemistry. Stars build heavy elements, supernovae distribute them, new stars and planets form from the enriched gas. Life, if it arises, is built from those elements, and when that life dies, the atoms return to the environment and eventually get swept up into the next generation of stars. It's a cycle that's been running for more than 13 billion years, and it will keep running for trillions more. Here's where we stand. You live on a planet orbiting a star. That star is one of hundreds of billions in a galaxy. That galaxy is one of hundreds of billions in the observable universe. The distances between objects grow as you zoom out. Earth to the Moon is 1 light second. Earth to the Sun is 8 light minutes. The solar system, defined by the Oort cloud, is about 1 light year across. The nearest star is 4 light years away. The nearest stars beyond that are scattered across distances of 5 to 10 light years. And we're still in the immediate neighborhood. We haven't even left the local bubble, a region of space about 1,000 light years across, where the density of stars is slightly higher than average. We haven't talked about the structure of the Milky Way, the spiral arms, the central bulge, the supermassive black hole at the core. We haven't talked about the other galaxies in our local group, Andromeda and the Magellanic Clouds and the dozens of dwarf galaxies scattered around us. We haven't talked about galaxy clusters or superclusters or the cosmic web that ties everything together. But before we get there, before we zoom out to the scale of galaxies and beyond, it's worth pausing on this scale, the scale of stars and planets, the scale where gravity and light are the dominant forces, the scale where distances are measured in light years instead of meters or kilometers, because this is the threshold. This is where human intuition finally gives up completely. You can imagine walking a kilometer. You can maybe imagine flying to the moon. You cannot imagine traveling 4 light years. Your brain has no framework for it. The numbers are too big. The timescales are too long. The emptiness is too vast. And this is just the beginning. The distances we've talked about so far, from Earth to Proxima Centauri, are nothing compared to what's coming. The Milky Way is 100,000 light years across. Andromeda is 2.5 million light years away. The observable universe stretches for 93 billion light years in every direction. We've barely started climbing the ladder. We're still on the lower rungs, looking up at a structure so tall that the top is beyond the reach of light itself. But that's the next step. That's where we're going. From stars to galaxies, from the solar system to the Milky Way, from the neighborhood to the city, from the handful of objects you can see with your naked eye to the billions of galaxies scattered across the cosmos, each one containing billions of stars, each star potentially hosting planets, each planet a world with its own history and chemistry and maybe, just maybe, its own life. The solar system is not the universe. It's barely a speck, but it's our speck. It's the place where we learned to look up, the place where we first measured the distance to the moon, then the distance to the sun, then the distance to the stars, and from those measurements we built a ladder that reaches all the way to the edge of everything we can see. That ladder starts here, with Earth, with the sun, with the slow realization that the sky is not a dome and the stars are not lights on a ceiling. They're distant suns, each one a furnace of fusion, each one separated from the next by gulfs of space so large that light itself struggles to cross them. And somewhere out there, scattered among those stars, are other planets, other worlds. Some hot, some cold, some rocky, some gaseous, some dead, some alive. We've only just started looking. We've found thousands of exoplanets orbiting other stars, and every one of them is a data point in the larger question of what the universe actually contains. How common are planets like Earth? How common is water? How common is life? We don't know yet. But the fact that we can ask the question at all, the fact that we can point a telescope at a star hundreds of light years away and detect the faint dip in brightness as a planet passes in front of it, is a staggering achievement. We've gone from measuring the distance to the moon to cataloging worlds in other star systems in less than a century. That's the power of the ladder. Once you start climbing, you don't stop. Each rung gives you the tools to reach the next one. Each new measurement expands the map, and the map keeps growing. From the solar system to the stars, from the stars to the galaxy, from the galaxy to the cosmos. The numbers get bigger, the distances stretch further, and somewhere in the middle of all that immensity, on a rock orbiting an average star in an unremarkable part of an ordinary galaxy, you sit and wonder what it all means. The answer, if there is one, is waiting at the top of the ladder. But to get there, we have to keep climbing. The next step is the Milky Way, our galaxy. The sprawling disk of stars and gas and dust that contains everything we've talked about so far and hundreds of billions of things we haven't. That's where we're going next, to the scale where individual stars stop mattering and the structures they form take over. To the place where distance is no longer measured in light years, but in kiloparsecs and megaparsecs. To the island of light we call home, floating in an ocean of darkness, so deep that even the brightest galaxies are just faint smudges against the black. The Milky Way is not a neighborhood, it's a city. A sprawling metropolis of light and gas and darkness stretching more than 100,000 light-years from edge to edge. And somewhere in the outer suburbs, about 26,000 light-years from downtown, on a quiet spiral arm that nobody pays much attention to, sits the sun. Our sun, the star you think of as bright and central and important. Out here in the galactic context, it's a dim streetlight on an unremarkable block in an unremarkable district of a city so large that light takes 100,000 years to cross from one side to the other. You live in a galaxy. That sentence should mean more than it does. You've heard the word galaxy your whole life. You've seen pictures, the Hubble Deep Field, the Andromeda Galaxy rising over a desert horizon, spiral arms glowing against the black. It all looks very pretty, very distant, very not your problem. But you are inside one of these things right now. Every star you've ever seen in the night sky, every constellation, every smudge of light the ancients turned into myths, all of it belongs to the Milky Way. You are not looking at the galaxy, you are looking through it. You are embedded in it the way a single cell in your body is embedded in tissue. And just like that cell, you have no perspective on the larger structure you're part of. You can't see the whole shape. You can only see your immediate surroundings and guess at the rest. The Milky Way is a spiral galaxy. That's a specific type, and it matters. Spiral galaxies have a flat disk of stars, gas and dust, rotating around a central bulge. Arms made of stars and nebulae wind outward from the center in a pattern that looks almost deliberate, like someone drew it with a compass. Our galaxy has at least 4 major spiral arms, maybe more. The exact number depends on how you define an arm versus a spur, and astronomers argue about it the way city planners argue about whether a street counts as a boulevard. The Sun sits on what's called the Orion Arm, sometimes called the Orion Spur, a minor feature connecting 2 larger arms. We are not on the main drag, we are on a side street. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range is wide because counting stars in a galaxy you're inside of is like trying to count the trees in a forest while standing in the middle of it. You can count the nearby ones. The distant ones blur together. Some are hidden behind dust. Some are too faint to detect. Some are embedded in clusters so dense that individual stars can't be resolved. Astronomers have done their best, and the best estimate sits around 200 billion stars, each one a sun. Some smaller, some larger, some brighter, some dimmer, each one burning hydrogen, fusing elements, pumping light and heat into the void. If you tried to count them, 1 per second, it would take you more than 6,000 years. 200 billion stars means 200 billion potential solar systems. We've only just started cataloging planets around other stars, and already we've found thousands. Most stars probably have planets. Some have many. Do the math and you're looking at hundreds of billions of worlds scattered across the galaxy. Rocky planets, gas giants, ice worlds, lava worlds. planets orbiting in the habitable zone where liquid water could exist, planets bathed in radiation, planets locked in tidal resonance, showing the same face to their star forever. Every configuration you can imagine and plenty you can't. And somewhere in that mix, statistically speaking, there should be others. Other worlds with liquid water, other worlds with chemistry complex enough to support life, other worlds where that life became complex enough to look up at the sky and wonder what else is out there. We don't know if they exist. We haven't found them yet. But the galaxy is big enough, old enough, and full enough that it would be stranger if we were alone. The Milky Way is old. Not as old as the universe, but close. The oldest stars in the galaxy formed about 13 billion years ago, less than a billion years after the Big Bang. Those stars are metal poor, meaning they contain almost no elements heavier than helium. They formed from the primordial gas left over from the early universe before supernovae had time to seed the cosmos with carbon, oxygen, and iron. Most of those ancient stars are gone now. They've burned out, exploded, or faded into white dwarfs. The ones that remain are small, dim red dwarfs tucked into the galactic halo, the roughly spherical cloud of old stars surrounding the disk. The halo is a graveyard. The disk is where the action is. The disk is about 1,000 light-years thick and 100,000 light-years across. It's where most of the galaxy's stars live, and it's where new stars are still being born. Star formation happens in nebulae, vast clouds of gas and dust, where gravity pulls material together until it gets dense enough and hot enough to ignite fusion. The Orion Nebula, one of the most famous star-forming regions visible from Earth, sits about 1,300 light-years away. It's a nursery, a factory. Dozens of new stars are being born there right now, this very moment, surrounded by disks of dust that will eventually coalesce into planets. Nebulae are enormous. The Orion Nebula spans about 24 light-years across. That's more than 5 times the distance from the Sun to Proxima Centauri, and it's just one of thousands. The Carina Nebula, the Eagle Nebula, the Tarantula Nebula, each one a furnace of creation, glowing with the light of young hot stars and the infrared heat of stars still forming inside clouds so thick that visible light can't escape. The James Webb Space Telescope has been peering into these regions, looking through the dust to see stars in the process of being born. What it's found is chaos. Stars don't form neatly. They form in clusters, blasting their surroundings with radiation and stellar winds that sculpt the gas into pillars and sheets and bubbles. The famous pillars of creation in the Eagle Nebula are columns of gas being eaten away by the light of nearby stars. In a few million years, they'll be gone. The stars inside them will remain. At the center of the Milky Way sits something that doesn't belong in polite company: a supermassive black hole. We've known it was there since the 1990s, when astronomers started tracking the orbits of stars near the galactic core. Those stars move fast, absurdly fast. Some of them complete an orbit in less than 20 years, whipping around an invisible point at speeds that reach a few % of the speed of light. The only thing that could make stars move that fast is a black hole. A big one. The black hole's name is Sagittarius A star, usually written as SGA A star. It weighs about 4 million times the mass of the Sun. Its event horizon is roughly 17 times the diameter of the Sun. For a black hole, that's not huge. Ton 618, the monster we talked about earlier, weighs 66 billion solar masses. SGA A star is a lightweight by comparison. But it's still a black hole sitting at the center of our galaxy, and it's close enough that we can watch stars orbit it. In 2022, the Event Horizon Telescope, a network of radio dishes scattered across the planet working together as a single instrument, released the first image of SGA A star. not the black hole itself. You can't photograph a black hole. It's black. What they photographed was the accretion disk, the glowing ring of gas and dust spiraling into the event horizon. The image showed a bright ring with a dark center, exactly what general relativity predicted. The dark center is the shadow of the black hole, the region where light gets bent so severely that it can't escape. The ring is the last photons, the light emitted by matter just before it crosses the point of no return. Most galaxies have supermassive black holes at their centers. It's become one of the standard features, like spiral arms or a central bulge. Nobody knows how they got there. The leading theory is that they grew over billions of years, fed by gas and stars falling into the core. Another theory suggests they formed early, maybe even before their host galaxies fully assembled, and the galaxies built up around them. Either way, the black holes are there, sitting quietly at the center of nearly every large galaxy we've observed. Some are actively feeding, pulling in gas and shining brightly as quasars. Others, like A star, are mostly dormant. There's not much gas near the galactic center anymore. The black hole is starving. It flares occasionally when something falls in, a star or a gas cloud. But most of the time it just sits there, a 4 million solar mass hole in space-time, waiting. The Sun orbits the galactic center once every 240 million years. That's one galactic year. The last time the Sun was in this part of the galaxy, dinosaurs were just starting to evolve on Earth. The next time it comes around, assuming Earth still exists, the Sun will have swollen into a red giant, and the planet will be a lifeless cinder. The orbit is not circular. It's slightly elliptical, and it bobs up and down relative to the galactic plane as it goes. Right now, the Sun is about 80 light-years above the midplane of the disk. In a few million years, it'll dip below. The motion is slow, imperceptible on human timescales, but it's there. The Sun is not stationary. None of the stars are. The entire galaxy is a swirling, rotating, gravitationally bound system, and every star in it is following its own long looping path through space. The Milky Way is not alone. It's part of a group. Astronomers call it the local group, and it contains more than 50 galaxies held together by gravity. Most of them are small, dwarf galaxies with a few billion stars or fewer. Some are satellites of the Milky Way, orbiting our galaxy the way moons orbit a planet. The Large Magellanic Cloud and the Small Magellanic Cloud are the two largest satellites, visible from the southern hemisphere as fuzzy patches of light. They're irregular galaxies, meaning they don't have a clean spiral or elliptical shape. They're just clumps of stars and gas being slowly torn apart by the Milky Way's gravity. Eventually they'll be absorbed, merged, eaten. The local group's largest member is not the Milky Way, it's Andromeda, also called M31. Andromeda is a spiral galaxy about 2.5 million light-years away. It's bigger than the Milky Way, containing about 1 trillion stars. Its spiral arms are tighter, more defined. It has its own supermassive black hole at the center, heavier than A star, weighing in at somewhere around 140 million solar masses. Andromeda has at least 14 satellite galaxies orbiting it, and like the Milky Way, it's been cannibalizing them over billions of years. 2.5 million light-years, that's the distance to Andromeda. It sounds enormous, and it is. Light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda through a telescope, you're seeing it as it was 2.5 million years ago, long before humans existed. But in galactic terms, 2.5 million light-years is close, uncomfortably close. Andromeda is our nearest large galactic neighbor, and it's heading toward us. The Milky Way and Andromeda are on a collision course. They're moving toward each other at about 110 kilometers per second. In about 4 billion years they will collide. Not in the way cars collide. Galaxies are mostly empty space. The stars in both galaxies will pass through each other like two clouds of gnats interpenetrating. Very few stars will actually hit each other. The distances between stars are so vast that even during a galactic collision, direct stellar collisions are rare. What will happen instead is that the gravitational interaction will distort both galaxies, pulling stars out of their orbits, flinging some into intergalactic space, dragging others toward the merged core. The spiral arms will shred. The disks will warp. Over the course of a few billion years, the two galaxies will merge into a single elliptical galaxy, a bloated football-shaped collection of stars with no spiral structure and very little gas left for forming new stars. Astronomers have named the future merged galaxy Milky. It's a terrible name, and it will never catch on, but it's what we're stuck with for now. By the time Milky forms, the Sun will be gone. It will have already left the main sequence, swelled into a red giant, and shed its outer layers. Whatever remains of Earth, if anything remains, will be orbiting a white dwarf in a galaxy that no longer looks anything like the one we grew up in. The night sky, assuming anyone is around to see it, will be unrecognizable. The constellations will have drifted. The nearby stars will be different. And overhead, the dense core of Milky will blaze with the light of billions of stars packed into a space far smaller than the Milky Way's current disk. There's a third large galaxy in the local group, Triangulum, also called M33. It's smaller than Andromeda and the Milky Way, with about 40 billion stars, and it sits about 3 million light-years away. Triangulum is also a spiral, and it's loosely bound to Andromeda. It might be a satellite. It might be in the process of falling toward Andromeda. It might be on its way to join the collision. Nobody knows for sure. Galactic orbits are hard to measure when you're inside the system, and the timescales are billions of years. The local group as a whole spans about 3 million light-years across. That's the rough diameter of the region where gravity keeps galaxies bound together. Beyond that, galaxies start to drift away, carried by the expansion of space itself. The local group is our neighborhood. It's the collection of galaxies close enough that gravity dominates over cosmic expansion. Everything inside the local group will eventually merge. Given enough time, trillions of years, the Milky Way, Andromeda, Triangulum, and all the dwarf galaxies will collapse into a single massive elliptical galaxy sitting alone in an expanding universe. But that's deep future. For now, the local group is a busy place. Galaxies are interacting, merging, pulling on each other. Dwarf galaxies are being tidally stripped, their stars stretched into long streams that wrap around the Milky Way like ribbons. Some of those streams have been mapped. The Sagittarius stream, for instance, is the remains of the Sagittarius dwarf elliptical galaxy, a small galaxy that's been orbiting the Milky Way for billions of years and is now being torn apart. Its stars are scattered across the sky in a faint arc that wraps all the way around the galactic disk. This is normal. This is what galaxies do. They grow by eating smaller galaxies. Galaxies are violent. The smooth pictures you see in textbooks are snapshots, moments of temporary calm in a process that's been running for more than 13 billion years. Every large galaxy has a history of collisions and mergers. The Milky Way has absorbed dozens of smaller galaxies over its lifetime. Andromeda has done the same. The scars are still visible in the form of stellar streams, disrupted clusters, and populations of stars with strange orbits that don't match the rest of the disk. Galactic archaeology is a real field. Astronomers study the positions, velocities, and chemical compositions of stars to reconstruct the Milky Way's history, to figure out which stars were born here and which ones were stolen from smaller galaxies that no longer exist. And then there's dark matter. We haven't talked about dark matter much yet because it's invisible and we have no idea what it's made of. But it's there. It has to be. The rotation curves of galaxies don't make sense otherwise. Here's the problem. When you measure how fast stars are moving at different distances from the galactic center, you expect the ones farther out to move slower. That's how gravity works. Planets farther from the sun orbit more slowly. Moons farther from a planet orbit more slowly. The same rule should apply to galaxies, but it doesn't. Stars at the edge of the Milky Way are moving just as fast as stars closer to the center. That shouldn't be possible unless there's more mass out there than we can see. A lot more. Dark matter is the name we give to that invisible mass. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. The only way we know it's there is through its gravitational effects. Dark matter outweighs ordinary matter by a factor of about 5 to 1. The Milky Way contains roughly 200 billion stars, but the total mass of the galaxy, including dark matter, is about 1.5 trillion times the mass of the Sun. Most of that mass is dark matter, forming a roughly spherical halo around the galaxy that extends far beyond the visible disk. We don't know what dark matter is. The leading candidates are exotic particles that don't interact with ordinary matter except through gravity. WIMPs, or weakly interacting massive particles, have been a popular guess for decades. Physicists have built detectors deep underground to try to catch dark matter particles colliding with ordinary atoms. So far, nothing. Axions are another candidate, hypothetical particles that are much lighter than WIMPs and would behave differently. Still nothing. Some physicists think dark matter might not be particles at all. Maybe gravity works differently on large scales than we think, and we're just seeing the effects of modified gravity rather than invisible matter. That idea has problems too, but it's on the table. The point is, galaxies are held together by something we can't see. The visible stars, gas and dust, are just the tip of the iceberg. The bulk of the mass is hidden, wrapped around the galaxy in a halo that shapes the orbits of everything inside it. Without dark matter, galaxies would fly apart. The stars at the edges would escape into intergalactic space. The spiral arms would unwind. The whole structure would collapse or disperse. Dark matter is the scaffolding. The visible matter is just decoration. The Milky Way, Andromeda, Triangulum, and all the dwarf galaxies in the local group are embedded in their own dark matter halos. Those halos overlap, interact, and pull on each other. The collision between the Milky Way and Andromeda isn't just a collision of stars and gas. It's a collision of dark matter halos, and the dark matter will merge first, pulling the visible galaxies along behind it like debris caught in a current. Galaxies are islands. That's the metaphor astronomers used for decades. Island universes, each one a separate system floating in the void. But the metaphor breaks down when you zoom out. Islands imply isolation. Galaxies are not isolated. They're part of larger structures. Groups like the local group. Clusters containing hundreds or thousands of galaxies. Superclusters containing dozens of clusters. And beyond that, the cosmic web, a vast network of filaments and voids stretching across the entire observable universe. We're standing on one island, looking out at the others. The Milky Way is home. Andromeda is the neighbor. Triangulum is the smaller house down the street. The dwarf galaxies are the cottages scattered around the neighborhood. But the neighborhood itself is part of a larger town, and that town is part of a city, and that city is part of a region so large that the word city stops making sense. Galileo Galilei pointed a telescope at the Milky Way in 1610 and realized it was made of stars. Thousands of faint stars, too dim to see individually with the naked eye, blending together into a glowing band across the sky. That was the first hint that the Milky Way was something more than a patch of glowing mist. Edwin Hubble took it further in 1929 when he measured the distances to other galaxies and realized they were receding from us. The farther away a galaxy was, the faster it moved. Space itself was expanding, carrying galaxies along with it. That discovery turned the universe from a static eternal structure into a dynamic evolving system with a beginning and, presumably, an end. We've come a long way since Galileo. We've mapped the Milky Way's spiral arms. We've measured the mass of its central black hole. We've counted its stars, catalogued its nebulae, tracked the orbits of its satellites. We've photographed Andromeda in exquisite detail, resolved individual stars in its outer regions, mapped its rotation, measured its approach. We've identified more than 50 galaxies in the local group and traced the gravitational interactions between them. We know the Milky Way is not special. It's one galaxy among hundreds of billions, maybe trillions, scattered across the observable universe. But it's our galaxy. It's the system we were born into, the structure that contains every star we've ever named, every planet we've ever discovered, every nebula we've ever photographed. It's the context for everything we've talked about so far. The Sun is a star in the Milky Way. The solar system is a speck in one of its spiral arms. Earth is a planet in that speck. You are a collection of atoms on that planet. And those atoms were forged in stars that lived and died billions of years ago, scattered across the galaxy by supernovae, swept up into new clouds of gas and dust, and eventually incorporated into the solar nebula that formed the Sun and planets 4.5 billion years ago. You are made of the Milky Way, literally. Every carbon atom in your body, every oxygen molecule you breathe, every calcium ion in your bones came from stars that exploded somewhere in this galaxy long before the Sun existed. You are not separate from the galaxy, you are part of it. A temporary arrangement of matter that happens to be self-aware, standing on a planet, looking up at the rest of the structure you belong to, trying to make sense of the scale. And the scale keeps growing. The local group is just the beginning. Beyond the 3 million light-year bubble that defines our immediate neighborhood, there are other groups, other clusters, other galaxies by the billions, organized into structures so large that they dwarf everything we've talked about so far. The Virgo cluster sits about 50 million light-years away and contains more than 1,000 galaxies. The Coma cluster is even larger, with thousands of galaxies packed into a region 100 million light-years across. And those clusters are themselves part of superclusters, vast filaments of galaxies stretching across hundreds of millions of light-years. The local group is falling toward one of those structures right now. A massive concentration of galaxies called the Virgo cluster, pulling us and everything around us in its direction. But the Virgo cluster is itself being pulled by something even larger, a gravitational anomaly so massive that it affects the motion of galaxies across a region hundreds of millions of light-years wide. Astronomers call it the Great Attractor, and it sits in a direction we can't see clearly because the disk of the Milky Way blocks the view. That's where we're going next, beyond the local group, beyond individual galaxies, to the scale where galaxies stop being objects and start being particles in a much larger fluid, to the clusters and superclusters and the vast cosmic currents that tie them together, to the structures so large that light takes hundreds of millions of years to cross them, to the place where the universe stops looking like a collection of islands and starts looking like a web. The Milky Way is not the universe, it's barely a thread in the tapestry. But it's the thread we can see most clearly. It's the one we've studied in the most detail. And from that thread, we've learnt how to read the rest of the pattern. The story of the Milky Way is the story of every galaxy: formation, growth, collisions, mergers, starbirth, star death, the slow accumulation of heavy elements, the invisible pull of dark matter holding everything together. It's a story that's been running for more than 13 billion years, and it's not finished yet. The Milky Way is falling. Right now, as you sit here, the entire galaxy is being pulled through space by something so massive that it bends the trajectory of hundreds of billions of stars. The Sun is not sitting still. Earth is not sitting still. The solar system is orbiting the galactic center at about 250 kilometers per second, and the galactic center itself is moving at roughly 600 kilometers per second toward a point in space about 200 million light-years away. You are not standing still. You are on a planet orbiting a star that's orbiting a galaxy that's falling toward something astronomers have been arguing about for decades. Welcome to the cosmic current. This is where individual galaxies stop being the main characters. This is where the story zooms out far enough that entire galaxies become particles, little specks of light swept up in gravitational flows so large that they operate on timescales longer than the age of complex life on Earth. The Milky Way is not alone. Andromeda is not alone. Every galaxy we've talked about so far, every spiral and elliptical and irregular blob of stars, is part of a larger structure, a network, a web. And that web is not static. It's moving, flowing, collapsing in some places, stretching in others, shaped by forces operating on scales that make galactic collisions look like fender benders. Let's start with clusters, because that's the first step up from individual galaxies. A galaxy cluster is exactly what it sounds like, a collection of galaxies held together by gravity. Not 2 or 3 galaxies like the local group, hundreds, sometimes thousands, all packed into a region of space tens of millions of light-years across, orbiting a common center of mass, pulling on each other, occasionally colliding, slowly merging into a single massive system. The nearest large cluster to us is the Virgo cluster. It sits about 50 million light-years away, which in galactic terms is close. Uncomfortably close. The Virgo cluster contains somewhere between 1,000 and 2,000 galaxies, depending on how you count the small ones. Most of them are elliptical galaxies, bloated football-shaped collections of old stars with very little gas left for forming new ones. Ellipticals dominate clusters because clusters are violent places. Galaxies collide more often in dense environments, and collisions destroy spiral structure. Merge 2 spirals and you get an elliptical. The Virgo cluster has been running this process for billions of years. It's a retirement home for galaxies that used to have arms and are now just smooth blobs of stars. The largest galaxy in the Virgo cluster is Messier 87, usually called M87. It's an elliptical giant weighing in at several trillion solar masses, making it one of the most massive galaxies in the nearby universe. M87 is also famous for hosting the first black hole ever directly imaged by the Event Horizon Telescope. The black hole weighs about 6.5 billion times the mass of the Sun, and the image released in 2019 showed exactly what general relativity predicted: a bright ring of glowing gas surrounding a dark shadow. That shadow is the event horizon, the point of no return. The black hole itself is invisible, but the light from the material falling into it is not, and that light has been traveling toward Earth for 50 million years. 50 million years ago, M87's black hole was glowing just as brightly as it is in the image. 50 million years ago, Earth was in the middle of the Eocene epoch. The climate was warm. There were no ice caps. Forests covered Antarctica. Early whales were starting to appear in the oceans. Primates were small and tree-dwelling. Nothing resembling a human existed, and light from M87 was beginning its journey across space, moving at 300,000 kilometers per second, crossing the gap between the Virgo cluster and the local group. While Earth's continents drifted, species evolved, climates changed, and entire ecosystems rose and fell. That light finally reached us in 2017, and we pointed a planet-sized telescope at it and turned it into a picture. The Virgo cluster is not the largest cluster we know about. It's not even close. The Coma cluster, about 300 million light-years away, contains more than 1,000 large galaxies and thousands of smaller ones. The Fornax cluster is smaller but denser. The Hercules cluster is larger but more diffuse. Clusters are common. The universe is full of them. And the reason clusters exist at all is because gravity wins on those scales. On small scales, the expansion of the universe dominates. Galaxies that are not gravitationally bound to each other drift apart as space expands. But in regions where the density of galaxies is high enough, gravity pulls them together into clusters. The clusters themselves are not expanding, they're collapsing, slowly, over billions of years, as galaxies fall toward the center of mass and merge. The space between galaxies in a cluster is not empty, it's filled with hot gas, extremely hot gas, tens of millions of degrees. The gas is so hot that it emits X-rays, and when astronomers point X-ray telescopes at galaxy clusters, they see enormous glowing clouds of gas filling the space between the galaxies. That gas is leftover material from the galaxies themselves, stripped away by collisions and interactions, heated by the gravitational energy of the cluster. Some of it will eventually cool and fall back into galaxies. Some of it will stay in intergalactic space forever, and beneath it all, holding the whole structure together, is dark matter. Lots of dark matter. Galaxy clusters are the best places to measure dark matter because the visible matter, the stars and gas, only accounts for about 15% of the total mass. The rest is dark. We know it's there because the galaxies are moving too fast. If you add up all the visible mass in a cluster and calculate how fast galaxies should be orbiting the center, the numbers don't match. The galaxies are moving 2 or 3 times faster than they should. The only explanation is that there's more mass than we can see, a lot more. The dark matter in a galaxy cluster forms a halo, a roughly spherical cloud of invisible mass that extends far beyond the visible galaxies. The galaxies are embedded in that halo like raisins in bread. The dark matter provides the gravitational scaffolding. The galaxies are just the decoration. Fritz Zwicky figured this out in 1933. He was studying the Coma cluster, measuring the velocities of galaxies and trying to calculate the cluster's total mass. The numbers didn't work. The galaxies were moving so fast that the cluster should have flown apart billions of years ago. Zwicky proposed that there must be invisible matter holding it together. He called it dark matter, and the astronomical community largely ignored him for decades. It wasn't until the 1970s when Vera Rubin measured the rotation curves of galaxies and found the same problem on smaller scales that dark matter became respectable. Now it's one of the pillars of cosmology. The universe contains about 5 times more dark matter than ordinary matter. We still don't know what it's made of, but we know it's there because without it, galaxy clusters wouldn't exist. Neither would galaxies. The universe would be a thin, diffuse soup of hydrogen with no structure at all. Clusters are big, tens of millions of light-years across. That's already a scale where human intuition gives up completely. But clusters are not the top of the hierarchy. Clusters themselves group together into superclusters, and that's where the numbers start to hurt. The Virgo cluster is part of the Virgo supercluster. The name is confusing because the Virgo supercluster is not just the Virgo cluster. It's a collection of about 100 galaxy groups and clusters spread across a region roughly 100 million light-years across. The local group is part of the Virgo supercluster, so is the Virgo cluster itself. So are dozens of other smaller groups scattered across the surrounding space. The Virgo supercluster is not a single bound object the way a galaxy or a cluster is. It's more like a neighborhood, a region where the density of galaxies is higher than average. Gravity is pulling galaxies within the supercluster toward the Virgo cluster, the densest part of the structure, but it hasn't had time to pull everything together yet. The supercluster is still in the process of collapsing. For decades, astronomers treated the Virgo supercluster as the Milky Way's address. Our galaxy was part of the local group, which was part of the Virgo supercluster, which was part of the observable universe. Simple, clean, wrong. In 2014, a team led by Brent Tully at the University of Hawaii published a new map of the local universe. Instead of mapping where galaxies are, they mapped where galaxies are going. They measured the velocities of more than 8,000 galaxies and traced the flow patterns. Galaxies don't move randomly. They move along currents, streams of motion shaped by the gravitational pull of dense regions and the repulsion of empty voids. Tully's team followed those currents backward to find the boundaries of gravitationally connected regions. What they found redrew the map. The Virgo supercluster is not a supercluster, it's a lobe, a subregion of a much larger structure that nobody had identified before because they were looking at positions instead of motions. The larger structure spans more than 500 million light-years and contains about 100,000 galaxies. Tully's team needed a name for it, and they chose a Hawaiian word, Laniakea. It means immeasurable heaven. Laniakea is enormous, 520 million light-years across. Light takes more than 500 million years to cross from one side to the other. The Milky Way sits near the outer edge of Laniakea, in a relatively sparse region far from the densest clusters. The center of Laniakea, the point toward which all the galaxies are flowing, is a region called the Great Attractor. That name is not poetic. It's descriptive. The Great Attractor is a gravitational anomaly so massive that it's pulling galaxies across hundreds of millions of light-years toward it. The Great Attractor was discovered in the 1970s when astronomers started measuring the velocities of nearby galaxies. They expected the galaxies to be moving more or less randomly, with a general outward motion due to cosmic expansion. What they found instead was a pattern. Galaxies in a huge region of the sky were all moving in the same direction, not away from us, toward something. The velocities were large, several hundred kilometers per second, and the direction was consistent across thousands of galaxies. Something out there was pulling, something big. The problem was that the Great Attractor sits in a part of the sky that's hard to observe. It's in the direction of the galactic center, which means it's behind the densest part of the Milky Way's disk. The disk is full of dust and gas, and that material blocks visible light. Astronomers call this region the zone of avoidance because there's a wedge of sky where we can't see distant galaxies. The Great Attractor sits right in the middle of that wedge. For years, astronomers knew something was there, pulling on the local universe, but they couldn't see it directly. Infrared and radio observations eventually pierced the dust and revealed what was hiding. The Great Attractor is not a single object. It's a cluster of clusters, a massive concentration of galaxies sitting about 200 million light-years away in the direction of the constellations Hydra and Centaurus. The region contains several large clusters, including the Norma cluster, one of the most massive clusters in the nearby universe. The combined mass of all those clusters creates a gravitational well deep enough to pull galaxies from hundreds of millions of light-years away. But here's the twist. The Great Attractor is not the end of the story. Tully's velocity map showed that the Great Attractor itself is being pulled by something even larger, a structure called the Shapley Supercluster, sitting about 650 million light-years away. The Shapley Supercluster is one of the most massive structures in the observable universe, containing more than 8,000 galaxies. It's pulling on the Great Attractor, which is pulling on Laniakea, which is pulling on the local group, which is pulling on the Milky Way. The universe is not a hierarchy of static objects. It's a cascade of gravitational flows, each layer pulling on the layer below, all of it driven by the distribution of dark matter left over from the early universe. This is where the cosmic web starts to come into focus. Galaxies are not scattered randomly through space. They're organized into filaments, long threads of galaxies stretching across hundreds of millions of light-years. The filaments connect clusters. The clusters sit at the intersections of filaments like beads on a string. Between the filaments are voids, vast regions of empty space where galaxies are rare. The voids are not completely empty. There are a few small galaxies scattered through them, but compared to the dense filaments and clusters, the voids are deserts. The structure is shaped by gravity and expansion. In the early universe, matter was almost perfectly smooth. Almost, but not quite. There were tiny density fluctuations, regions where the matter was slightly denser or slightly less dense than average. Those fluctuations were imprinted by quantum processes in the first fraction of a second after the Big Bang. Over time, gravity amplified the fluctuations. Dense regions pulled in more matter and became denser. Sparse regions lost matter and became sparser. Over billions of years, the denser regions collapsed into filaments and clusters. The sparser regions expanded into voids. The result is the cosmic web, a three-dimensional network of structure that looks like foam, dense walls and filaments surrounding empty bubbles. Laniakea is one cell in that foam, one region where the density is high enough that gravity has organized galaxies into a coherent flow pattern. The boundaries of Laniakea are not walls, they're watersheds, points where the gravitational flow changes direction. On one side of the boundary, galaxies are flowing toward the Great Attractor. On the other side, they're flowing toward a different attractor in a different supercluster. The boundaries are real in the sense that they mark a transition in the motion of galaxies, but they're not sharp. There's no edge, just a gradual shift in velocity as you move from one basin of attraction to another. The flows are slow. Galaxies are not zipping around at relativistic speeds. A few hundred kilometers per second sounds fast, and it is by human standards, but on cosmic scales it's glacial. The Great Attractor is pulling the Milky Way at about 600 kilometers per second. At that speed, it would take the Milky Way about 100 billion years to reach the Great Attractor. By then, the universe will be unrecognizably different. The Sun will be long dead. The Milky Way will have merged with Andromeda. The cosmic expansion, driven by dark energy, will have stretched space so much that distant galaxies will have receded beyond the cosmic horizon. The Great Attractor will still be out there, but it won't matter because nothing will be able to reach it. That's the key tension on these scales. Gravity pulls galaxies together. Dark energy pushes space apart. On small scales, gravity wins. Galaxy clusters are collapsing. Laniakea is collapsing. The local group is collapsing. But on larger scales, dark energy dominates. Superclusters that are not gravitationally bound are being pulled apart by the expansion of space. The distance between Laniakea and the Shapley Supercluster is growing, not shrinking. Eventually, the expansion will win everywhere. Clusters will merge into single massive galaxies, and those galaxies will drift apart into isolation. The cosmic web will dissolve. The universe will become a collection of island galaxies separated by voids, so large that light will never cross them. But that's trillions of years in the future. For now, the web is intact. The flows are running. Galaxies are falling along filaments toward clusters. Clusters are falling toward superclusters. And the whole structure is visible in surveys like the Sloan Digital Sky Survey, which has mapped the positions and velocities of millions of galaxies. When you plot those galaxies in 3 dimensions, the web jumps out. Bright filaments connecting clusters, dark voids in between. The pattern repeats across the entire observable universe. The same structure at every scale, filaments and voids, clusters and superclusters, all of it shaped by the same process, gravity amplifying the tiny fluctuations left over from the Big Bang. The cosmic web is not unique to our part of the universe. It's everywhere. Every region of space large enough to contain thousands of galaxies shows the same structure. Filaments, clusters, voids, the details differ. Some filaments are thicker, some voids are larger, but the overall pattern is universal. The universe is a web, not a smooth distribution, not a random scatter, a web. And here's the uncomfortable part. We're inside it. The Milky Way is not sitting outside looking at the cosmic web the way you look at a map. The Milky Way is part of the web. A single galaxy in one filament, in one supercluster, in one small corner of the observable universe. Every measurement we make, every velocity we calculate, every structure we map is done from inside the system. We can't step outside. We can't see the web from a neutral vantage point. We have to reconstruct the larger structure from the motion of galaxies around us, and that reconstruction is always incomplete because we can only measure galaxies close enough to see and only in directions where the Milky Way's disk isn't blocking the view. The zone of avoidance is still there. We've pierced it with infrared and radio observations, but we still don't have a complete map of what's hiding behind the galactic disk. There could be structures we've missed, clusters we haven't catalogued, flows we haven't measured. The map of Laniakea is the best map we have, but it's not perfect. It's a snapshot based on the velocities of 8,000 galaxies, which sounds like a lot but is a tiny fraction of the total number of galaxies in the region. Most galaxies are too faint or too obscured to measure. The map is an approximation, a sketch. The real structure is more complicated. Dark energy complicates everything. On small scales where gravity is strong, dark energy doesn't matter much. Galaxies in a cluster are held together by gravity despite the expansion of space. But on larger scales, dark energy dominates. It's the reason the universe's expansion is accelerating. It's the reason distant galaxies are receding faster than the speed of light. And it's the reason superclusters will eventually dissolve. Dark energy is a property of space itself. The more space there is, the stronger its effect. As the universe expands, dark energy becomes more important, and gravity becomes less important. Eventually, dark energy will win everywhere. The cosmic web will stretch and thin until it disappears. We don't know what dark energy is. That's not a comforting statement, but it's the truth. We've measured its effects. We know it's causing the expansion of the universe to accelerate. We know it accounts for about 68% of the total energy density of the universe. But we don't know what it's made of or why it exists. The leading theory is that it's the energy of empty space, a property predicted by quantum field theory called vacuum energy. But the predicted value of vacuum energy is so enormously larger than the observed value of dark energy that calling them the same thing requires explaining why they differ by a factor of 10 to the power of 120. That's not a small discrepancy. It's the largest discrepancy in the history of physics. Another possibility is that dark energy is not constant. Maybe it changes over time. Maybe it's a field, like the Higgs field, with its own dynamics. Astronomers are testing this by measuring how the expansion rate has changed over the history of the universe. If dark energy is constant, the acceleration should follow a specific pattern. If it's dynamic, the pattern will be different. So far, the data is consistent with constant dark energy, but the uncertainties are large enough that other models are still on the table. What's clear is that dark energy is real and it's shaping the future of the universe. Clusters will survive because they're dense enough that gravity can hold them together, but the space between clusters will keep expanding. Superclusters will be pulled apart. The filaments of the cosmic web will stretch and fade. In 1 trillion years, an astronomer in a galaxy that used to be part of Laniakea will look out into the night sky and see nothing. No distant galaxies, no cosmic web, no evidence that the universe is anything more than a single isolated galaxy surrounded by endless empty space. All the other galaxies will have receded beyond the cosmic horizon. Their light will never reach the observer because the space between them is expanding faster than light can cross it. We live at a special time, not special in the sense that the universe was designed for us or that we're cosmically important. Special in the sense that we happen to exist during the narrow window when the cosmic web is visible. A few billion years ago, the universe was smaller and denser, and the web was harder to see because galaxies were closer together and the structures were less developed. A few billion years from now, the universe will be larger and sparser, and the web will start to fade as expansion pulls the filaments apart. We're seeing the web at its peak, the moment when it's most clearly defined. And we're seeing it from inside, trying to map the structure we're embedded in, measuring the flows we're caught up in, tracing the gravitational currents that have been pulling galaxies around for billions of years and will keep pulling them until dark energy wins and the currents stop. The Great Attractor is still pulling. Laniakea is still collapsing. The local group is still falling. And somewhere in the middle of all that motion, on a planet orbiting a star in a galaxy on the edge of a supercluster, being pulled toward a gravitational anomaly 200 million light-years away, you're sitting still, or at least you think you are. Because from your perspective, the ground is solid, the chair is stationary, and the room is not moving. But the planet is rotating. The planet is orbiting the sun. The sun is orbiting the galactic center. The galactic center is being pulled by the Virgo cluster. The Virgo cluster is being pulled by the Great Attractor. The Great Attractor is being pulled by the Shapley Supercluster. And all of it is embedded in the expanding fabric of space, carried along by dark energy, drifting toward a future where every structure we've talked about will be an isolated island in a sea of nothing. The web is fragile, it's temporary. It exists because the universe is old enough for gravity to have organized matter into structure, but young enough that dark energy hasn't torn the structure apart yet. In cosmic terms, we're in the middle, not at the beginning, not at the end, halfway through the story. And the story we're reading is written in the motion of galaxies, the distribution of dark matter, and the tension between gravity and expansion playing out on scales so large that entire superclusters are just details in the pattern. This is the scale where galaxies stop being individuals and start being fluid, where the Milky Way is not a thing but a particle in a current, where Andromeda is not a neighbor but another drop of water in the same stream, where the local group is not a family but a piece of debris caught in a flow that stretches across 500 million light-years. The cosmic web is not made of solid threads, it's made of galaxies, billions of them, and every one of those galaxies is made of billions of stars. And every one of those stars is a furnace of fusion surrounded by a system of planets and moons and asteroids. And somewhere in all that structure, On one planet, in one system, in one galaxy, in one supercluster, life arose. And that life is now looking outward, measuring the web, tracing the flows, trying to understand how it all fits together. The web is the answer, not the final answer, but the next layer. The structure that connects galaxies into something larger. The pattern that emerges when you zoom out far enough that individual galaxies blur together into points of light. And the web itself is just the beginning. Because beyond the clusters and superclusters, beyond Laniakea and the Great Attractor, there's more. More filaments, more voids, more structure stretching all the way to the edge of the observable universe. The cosmic web is not a local phenomenon, it's universal, and the only way to see it, the only way to understand what the universe actually looks like on the largest scales, is to keep zooming out. To step back from the clusters and the flows and look at the full picture, the whole web, every filament and void, every galaxy and every empty space, the entire observable universe laid out in 3 dimensions, showing the structure that gravity built over 13 billion years of cosmic history. That's where we're going next, to the largest scales, to the edge of what we can see, to the voids and the filaments and the ancient light from the first galaxies, to the cosmic dawn and the end of everything observable. The web is waiting. We've been climbing, from quarks to atoms, atoms to cells, cells to planets, planets to stars, stars to galaxies, galaxies to clusters, clusters to superclusters. Each step up the ladder, the numbers got bigger, the distances stretched further, and the structures became less familiar. You started on solid ground. You ended up watching entire galaxy clusters fall through space like leaves in a current. And now we're going to take one more step, the last step before the edge, the step where individual galaxies, clusters, even superclusters, stop being the main story and become tiny details in a pattern so large that it took billions of years to form and will take billions more to fade. This is the cosmic web, the largest known structure in the universe. A 3-dimensional network of filaments and voids stretching across the entire observable cosmos. It's not a thing you can point to. It's not an object sitting out there waiting to be photographed. It's a pattern, a distribution. The way matter has organized itself over the last 13.8 billion years under the relentless pull of gravity and the equally relentless push of cosmic expansion. And it's the closest thing the universe has to a skeleton. Imagine a sponge, not a kitchen sponge, a natural sea sponge. The kind with holes and tunnels running through it in every direction. Thin walls separating empty spaces, dense intersections where multiple walls meet. Now imagine that sponge is 500 million light-years across. The walls are made of galaxies. The holes are empty. The intersections are galaxy clusters. That's the cosmic web, foam-like, lacy, delicate in appearance but held together by forces strong enough to organize hundreds of billions of galaxies into a coherent pattern. The walls are called filaments, long threads of galaxies stretching across tens or hundreds of millions of light-years. The empty spaces are called voids, vast bubbles of mostly nothing where galaxies are rare. The intersections where filaments meet are clusters and superclusters, the densest regions of the web where thousands of galaxies pile up under their own gravity. The whole structure repeats at every scale you look. Small voids a few million light-years across. Larger voids hundreds of millions of light-years across. Thin filaments connecting small clusters. Thick filaments connecting superclusters. The pattern is fractal, self-similar. Zoom in or zoom out and you see the same basic architecture. Walls and bubbles, dense and empty, structure and void. The cosmic web is not a metaphor. It's a real physical structure that exists in three-dimensional space. Astronomers have mapped it by measuring the positions and distances of millions of galaxies. When you plot those galaxies in 3 dimensions, the web jumps out immediately. You don't have to squint. You don't have to apply filters or smooth the data. The structure is obvious. Bright filaments snaking across space, connecting clusters like roads connecting cities, dark voids in between, enormous empty regions where almost nothing lives. The web is the answer to a question nobody thought to ask until the 1980s. What does the universe look like when you zoom out far enough that galaxies become pixels? It looks like foam. The first hints of large-scale structure came in the late 1970s and early 80s, when astronomers started mapping the distribution of galaxies in 3 dimensions. Before that, most surveys only measured positions on the sky, 2-dimensional maps. Useful, but incomplete. Distance is the 3rd dimension, and without it you can't tell if 2 galaxies that appear close together in the sky are actually neighbors or just happen to line up from our point of view. Measuring distance requires measuring redshift, the stretching of light caused by the expansion of space. Light from distant galaxies gets stretched to longer wavelength as space expands. The more stretched the light, the farther away the galaxy. Measure the redshift, calculate the distance, and you've got the 3rd dimension. In 1986, Valerie de Lapparent, Margaret Geller, and John Huckra published a map of about 1,000 galaxies in a thin slice of the sky. The map covered a region extending out to about 500 million light-years. When they plotted the galaxies, they expected to see a more or less random distribution with maybe some clumping around clusters. What they saw instead was a pattern that looked like soap bubbles. Galaxies arranged along thin sheets and filaments surrounding large empty regions. The voids were huge, 50 to 100 million light-years across, and they were everywhere. One of the voids in their map, later called the coma void, was so large and so empty that it immediately became clear the universe was not a smooth distribution of galaxies. It was bubbly, foamy, structured in a way nobody had predicted. Geller called the structures they found the Great Wall. Not because it was a single wall, but because one of the filaments in their data stretched across the entire length of their survey, more than 500 million light-years, without a break. It was the largest structure known at the time, and it was just the beginning. As surveys got larger and deeper, more walls appeared, more voids, more filaments. The pattern repeated everywhere. Every patch of sky showed the same thing. Walls of galaxies surrounding empty bubbles. No matter which direction you looked, the web was there. The Sloan Digital Sky Survey, launched in 2000, mapped more than 1 million galaxies across a huge volume of space. When the data was plotted, the cosmic web became undeniable. Filaments tens of millions of light-years long connecting clusters. Voids hundreds of millions of light-years across. Superclusters sitting at the intersections of multiple filaments like highway interchanges. The web was not a local phenomenon, it was universal. Every region of the observable universe large enough to map showed the same structure. Walls and voids, dense and empty. The cosmic web was the fundamental architecture of the cosmos. So where did it come from? Why is the universe structured this way, instead of being a smooth, uniform distribution of galaxies scattered randomly through space? The answer takes us back to the beginning, to the Big Bang, to the first moments after the universe began expanding from a hot, dense state 13.8 billion years ago. In the very early universe, matter was almost perfectly smooth, almost, but not quite. There were tiny density fluctuations, regions where the matter was slightly denser or slightly less dense than average. Those fluctuations were incredibly small, 1 part in 100,000. A density difference so tiny that if you could have measured the temperature of the early universe in different directions, you'd find variations of only a few millionths of a degree. But those tiny variations were enough. Gravity amplified them. Dense regions pulled in more matter. As they pulled in more matter, they became denser. As they became denser, their gravity got stronger. As their gravity got stronger, they pulled in even more matter. Feedback loop. The rich got richer. Sparse regions, meanwhile, lost matter. The gas and dark matter in those regions drifted toward the denser regions, leaving the sparse regions even emptier. Over time, the denser regions collapsed into filaments and clusters. The sparse regions expanded into voids. The process took billions of years, but the end result was the cosmic web we see today, a network of dense filaments and sheets surrounding vast empty bubbles. The fluctuations themselves, the tiny density variations that seeded the cosmic web, came from quantum processes in the first fraction of a second after the Big Bang. During a period called inflation, the universe expanded exponentially, doubling in size every tiny fraction of a second. Quantum fluctuations in the fields driving inflation got stretched to macroscopic scales and froze into the fabric of space as tiny density variations. Those variations were imprinted on the distribution of matter and radiation in the early universe. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, the density variations left an imprint on the cosmic microwave background. The CMB is the relic radiation from that era, the first light that could travel freely through space once the universe became transparent. And when astronomers measure the CMB, they see those tiny temperature fluctuations, 1 part in 100,000. Hot spots and cold spots scattered across the sky in a pattern that matches the initial conditions needed to grow the cosmic web. The CMB is a baby picture of the universe, a snapshot of what the cosmos looked like when it was 380,000 years old. The temperature fluctuations in that snapshot are the seeds of everything that came after. Galaxies, clusters, superclusters, filaments, voids, all of it grew from those tiny ripples in the density of the early universe. The cosmic web contains statistical memory of the Big Bang. It's a record of the initial conditions written in the positions and motions of galaxies billions of years later. Here's the scale we're talking about. The observable universe is about 93 billion light-years across. That's the diameter of the region from which light has had time to reach us since the Big Bang. It's not the size of the entire universe. The universe might be infinite. It might be much larger than the observable part. We don't know. We can't see beyond the observable horizon because light from farther away hasn't had time to reach us yet. But the observable universe alone is enormous. 93 billion light-years. Light takes 93 billion years to cross from one side to the other, except the universe is only 13.8 billion years old. How does that work? Expansion. The universe has been expanding the entire time the light was traveling. A galaxy sitting at the edge of the observable universe today emitted its light 13.8 billion years ago, shortly after the Big Bang. That light has been traveling toward us ever since, but while it was traveling, space was expanding. The galaxy moved farther away. By the time the light reaches us, the galaxy is no longer 13.8 billion light-years away. It's 46 billion light-years away, and the distance from us to the opposite edge of the observable universe is twice that. 93 billion light-years. The observable universe is larger than you'd expect because space itself has been stretching while light was in transit. The cosmic web fills that entire volume. From one side of the observable universe to the other, galaxies are organized into filaments and voids. The pattern doesn't stop at the edge of what we can see. It keeps going. The observable universe is just the part we can access with telescopes. Beyond the horizon, the web continues. Filaments stretching into regions we'll never be able to observe because the light from those regions will never reach us. The universe is bigger than what we can see, and the web is bigger too. The filaments themselves are made mostly of dark matter. The galaxies we see are just traces, markers showing where the dark matter is densest. Dark matter doesn't emit light. It doesn't interact with electromagnetic radiation at all, but it interacts with gravity, and gravity is what built the web. Dark matter collapsed first, pulling ordinary matter along with it. The dark matter formed the scaffolding. The gas followed the dark matter into the filaments and clusters, where it eventually formed stars and galaxies. The galaxies we observe today are embedded in filaments of dark matter stretching across hundreds of millions of light-years. The visible matter is the decoration. The dark matter is the structure. Filaments are not thin. A typical filament is tens of millions of light-years long and several million light-years thick. They're packed with galaxies, thousands of them strung along the length of the filament like beads on a thread. The galaxies are not evenly spaced. They clump together in groups and clusters at certain points along the filament, and the densest clumps sit where multiple filaments intersect. Those intersections are the superclusters we talked about in the last chapter. Laniakea is one of those intersections. The Great Attractor sits at a point where several filaments meet, and the combined gravity of all the dark matter and galaxies in those filaments is what's pulling everything nearby toward it. The voids are even more interesting. They're enormous. The largest known voids are more than 1 billion light-years across. 1 billion light-years. Light takes 1 billion years to cross from one side to the other. Inside those voids, galaxies are rare, not completely absent, but sparse. The density of galaxies in a void is about 10% of the average density in the universe. Most of the volume of a void is empty space, just a thin haze of hydrogen gas and dark matter, so diffuse it's effectively a vacuum. The voids are not expanding faster than the rest of the universe. They're not being pushed open by some mysterious force. They're just regions where the initial density was slightly lower than average, and over billions of years gravity pulled matter out of those regions and into the surrounding filaments. The voids are the leftovers, the spaces between the structure, and they're growing. As the universe expands, the voids get bigger, the filaments stretch. The clusters at the intersections are still collapsing because their gravity is strong enough to overcome the expansion, but the space between clusters is growing. The web is being pulled apart slowly by the expansion of space. Dark energy, the mysterious force driving the accelerated expansion of the universe, is winning on large scales. Eventually, trillions of years from now, the voids will be so large that galaxies in different filaments will lose sight of each other. The light won't be able to make the journey because space will be expanding faster than light can cross it. The cosmic web will dissolve. The filaments will snap. The universe will become a collection of isolated clusters, each one surrounded by an ever-growing void, drifting alone through an expanding cosmos. But that's the far future. For now, the web is intact, and we can see it not just as a map of galaxies, but as a map of light and gas and even gravitational distortion. One of the most powerful tools for mapping the cosmic web is gravitational lensing. Mass bends space. Light traveling through bent space follows a curved path. If a massive filament of dark matter sits between us and a distant galaxy, the light from that galaxy gets bent as it passes through the filament. The galaxy's image gets distorted, stretched into an arc, or split into multiple images. By measuring the distortion, astronomers can map the distribution of dark matter in the filament, even though the dark matter itself is invisible. Lensing surveys have mapped the dark matter web in stunning detail, confirming that the visible galaxies sit exactly where the dark matter is densest. Another tool is the Lyman alpha forest. Lyman alpha is a specific wavelength of light emitted by hydrogen when an electron drops from the second energy level to the first. In the early universe, before galaxies had time to reionize all the hydrogen, there were vast clouds of neutral hydrogen scattered through space. Light from distant quasars, the bright cores of actively feeding black holes, passes through those hydrogen clouds on its way to us. Each cloud absorbs a bit of the light at the Lyman alpha wavelength, leaving a dark line in the spectrum. A quasar shining through multiple clouds shows multiple absorption lines, a forest of lines stacked together. By measuring where those lines appear in the spectrum, astronomers can map the distribution of hydrogen gas along the line of sight to the quasar, and the hydrogen gas traces the filaments. The Lyman alpha forest is a map of the cosmic web as it existed billions of years ago, when the light was passing through those clouds on its way to Earth. The web looked different in the past. It was less developed, less defined. Galaxies were closer together, the voids were smaller, the filaments were thicker. Over time, as the universe expanded and structure continued to collapse under gravity, the web became more pronounced. The voids grew, the filaments thinned, the clusters became denser. The cosmic web we see today is a snapshot of a process that's been running for more than 13 billion years and will keep running for trillions more. And then there's the cosmic dawn, the era when the first stars and galaxies formed, the period between about 100 million and 1 billion years after the Big Bang, when the universe transitioned from a dark neutral fog to a transparent ionized medium lit up by the light of young galaxies. Before cosmic dawn, the universe was dark. There were no stars. The hydrogen gas filling space was neutral, meaning it absorbed light instead of letting it pass through. The first stars changed that. They were massive, hot, and short-lived. They pumped out ultraviolet radiation intense enough to ionize the hydrogen around them, creating bubbles of transparency. As more stars formed, the bubbles grew and merged. Eventually, the entire universe was reionized. The fog cleared. Light could travel freely. Galaxies became visible. The James Webb Space Telescope was built to study cosmic dawn. Its infrared sensors can see the light from the first galaxies, stretched into the infrared by the expansion of space. Webb has found galaxies at redshifts higher than 13, meaning we're seeing them as they existed less than 400 million years after the Big Bang. Those galaxies are small, messy, and bright. They're forming stars at a furious rate, building up mass faster than models predicted. Some of them are brighter than they should be, suggesting either that they're forming stars more efficiently than modern galaxies, or that they harbor massive black holes feeding on gas and outshining the stars around them. Either way, cosmic dawn was not a quiet era. It was violent, chaotic. The first galaxies were colliding, merging, and blasting their surroundings with radiation. The web was starting to form, but it was barely visible, just hints of structure in a universe still dominated by smooth, diffuse gas. Over the next few billion years, those hints became filaments. The filaments became walls. The walls surrounded voids, and by the time the universe was a few billion years old, the cosmic web looked recognizably like the web we see today. The process didn't stop. It's still running. Clusters are still collapsing. Voids are still growing. The web is still evolving. But the basic architecture was set early. The seeds planted in the first fraction of a second after the Big Bang grew into the largest structures in the universe. Here's the thing that breaks your brain. The cosmic web is not a designed structure. Nobody built it. There was no blueprint. no plan. It's an emergent pattern, the inevitable result of gravity acting on matter in an expanding universe with tiny initial density fluctuations. You start with a smooth distribution of matter with 1 part in 100,000 variations. You let gravity pull the dense regions together and push matter out of the sparse regions. You wait 13 billion years and you get the cosmic web, walls, filaments, voids, the largest coherent structure in the observable universe, all of it grown from quantum fluctuations in the first fraction of a second after the Big Bang. The web is not random, but it's not ordered either. It's somewhere in between. Statistical, predictable in broad strokes but unique in detail. You can simulate the formation of the cosmic web on a computer. Start with the initial conditions from the CMB, add dark matter and ordinary matter, turn on gravity, let the simulation run forward in time. The result matches the observed universe almost perfectly. Filaments in the right places, voids the right size, clusters at the right intersections. The match is so good that cosmologists use simulations to test theories about dark matter and dark energy. If a simulation produces a web that doesn't match observations, the theory is wrong. The web is also a tool. Astronomers use it to measure the expansion history of the universe. There's a feature in the cosmic web called baryon acoustic oscillations, BAO for short. In the early universe, before atoms formed, matter and radiation were coupled together. Pressure waves, sound waves essentially, rippled through the hot plasma. When atoms finally formed and the universe became transparent, those pressure waves froze into the distribution of matter. The result is a slight excess of galaxies at a specific distance from other galaxies, about 500 million light-years. That distance is the sound horizon, the maximum distance a sound wave could have traveled in the early universe before atoms formed. By measuring the BAO feature in the distribution of galaxies today, astronomers can determine how much the universe has expanded since the early universe. It's a standard ruler, a known distance imprinted on the cosmic web that can be compared at different eras to measure how fast space has been expanding. BAO measurements confirm that the expansion of the universe is accelerating. Dark energy is real, it's pushing galaxies apart, and it's going to win. In the long run, the cosmic web will dissolve. The filaments will stretch until they're no longer connected. The voids will grow until they're larger than the observable universe is now. Clusters will merge into single giant galaxies, and those galaxies will drift apart until each one is alone, surrounded by nothing but expanding emptiness. The universe will become a cold, dark, lonely place where the only light comes from the dying embers of stars that burned out trillions of years ago. But we're not there yet. We're here now in the middle of the story. The cosmic web is visible. The clusters are collapsing. The filaments are intact. Galaxies are still forming stars. Black holes are still feeding. The universe is still young enough and dense enough that structure is growing, not fading. This is the era when the web is at its most beautiful, when the contrast between dense filaments and empty voids is sharpest, when the pattern is clear enough to map, but complex enough to hide surprises. And there are surprises. Every new survey finds structures that don't quite fit, filaments that are longer than expected, voids that are emptier, clusters that are denser. The cosmic web is not a static pattern. It's dynamic, evolving, full of details that challenge the models and force astronomers to refine their understanding of how structure forms. The web is a laboratory, a natural experiment running on scales so large that we can't reproduce it. All we can do is watch, measure, map, and try to understand how a universe that started almost perfectly smooth ended up looking like foam. The web is also a reminder, a humbling, uncomfortable reminder that the scales we've been climbing are real. You started at the Planck length, the smallest meaningful distance in physics. You've climbed 45 orders of magnitude, 45 factors of 10, from 10 to the power of negative 35 meters to 10 to the power of 10 meters, the size of the cosmic web filaments. You've crossed from the quantum realm, where particles don't have definite positions, to the cosmic realm, where galaxies are just pixels in a pattern. And at every step, the structures got larger, the timescales got longer, and your intuition became less useful. The cosmic web is the edge of structure. Beyond it, there's only the expansion of space itself, the horizon, the limit of what we can see, the boundary between the observable and the unobservable. And that boundary is not a wall. It's not an edge you can point to. It's a consequence of the finite speed of light and the finite age of the universe. Light from beyond the horizon hasn't had time to reach us yet. It never will. The expansion of space is carrying those regions away faster than light can catch up. The cosmic web continues beyond the horizon, but we'll never see it. The universe is bigger than we can ever observe, and the structures beyond our reach, the filaments and voids and clusters that exist in regions we'll never be able to map, might be different. Stranger, built on the same rules but arranged in configurations we can't predict because we don't have the data. That's the final uncomfortable truth. The cosmic web we see, the largest structure we've mapped, the pattern that spans the entire observable universe, is just a piece, a sample, one region of a cosmos that might be infinite or might be finite but so large that the word large stops meaning anything. We're inside the structure, we're part of the web, and we're trying to understand the whole pattern from a single vantage point, using instruments that can only see light, measuring objects that are billions of light years away and billions of years in the past, reconstructing a three-dimensional structure from two-dimensional images and one-dimensional spectra. And somehow, impossibly, it's working. The map is incomplete, but it's accurate. The cosmic web is real. The filaments are there. The voids are there. The pattern is universal. And we've figured it out in less than a century of serious effort. From Hubble's discovery of cosmic expansion in 1929 to the Sloan Digital Sky Survey's three-dimensional maps of millions of galaxies in the 2000s, we've gone from not knowing other galaxies existed to mapping the large-scale structure of the entire observable universe. That's where we are, standing at the top of the ladder, looking out at the web, knowing that it extends beyond what we can see but unable to go any further. The cosmic web is the answer to what the universe looks like on the largest scales. It's the structure that gravity built, the pattern that emerged from tiny quantum fluctuations in the first moments after the Big Bang, the scaffolding that holds galaxies and clusters and superclusters together and separates them with vast empty voids. It's the skeleton of the cosmos, the framework everything else is built on. And now there's only one question left. What happens when you reach the edge? Not the edge of the web, the edge of the observable universe, the horizon where light runs out of time, the boundary between what we can see and what we can't, the place where the map ends and the unknown begins. That's the last step, the final chapter. The place where numbers stop working and you're left with infinity and the uncomfortable realization that everything we've talked about, every scale from quarks to cosmic voids, is just the part we can measure, the part that fits inside the observable universe. Beyond that, there's more, always more, and we'll never know how much. We've reached the edge. Not the edge of a cliff or a coastline or anything you could stand on and peer over. The edge of what we can see, the boundary where light runs out of time, the horizon beyond which the universe exists but refuses to show itself. And standing here, at the top of the ladder we've been climbing for 6 chapters, the view is not comforting, because the edge is not an answer, it's a question. And the question is simple, brutal, and maybe unanswerable. What's beyond it? The observable universe is 93 billion light-years across. That number has been rattling around in your head since the title of this video. 93 billion light-years. It's enormous, incomprehensible. The kind of distance that makes galactic superclusters look like grains of sand on a beach. But here's the part nobody tells you until you're already committed to the climb. The observable universe is not the universe, it's just the part we can see. The part where light has had enough time since the Big Bang to reach us. Beyond that horizon, the universe keeps going. How far? We don't know. Maybe a lot farther. Maybe infinitely farther. Maybe the observable universe, this 93 billion light-year bubble we've spent billions of dollars mapping, is a drop of water in an ocean that has no shore. Let's start with the horizon itself, because the edge of the observable universe is one of the strangest concepts in physics. It's not a wall. It's not a boundary you could fly a spacecraft toward and eventually reach. It's a consequence of time and the speed of light. The universe is 13.8 billion years old. That's how long it's been since the Big Bang. Light is fast, the fastest thing there is, but it's not infinitely fast. It travels at about 300,000 kilometers per second. In 13.8 billion years, light can only travel so far. If the universe were static, not expanding, light from the Big Bang would have traveled about 13.8 billion light-years in every direction, and the observable universe would be about 27.6 billion light-years across. Simple multiplication. Except the universe is not static. It's been expanding the entire time. Here's how that works. Imagine you're standing on a moving walkway at an airport, the kind that carries you along while you stand still. Now imagine you start walking forward on that walkway. You're moving relative to the walkway, and the walkway is moving relative to the floor. Your total speed relative to the floor is the sum of both motions. Light in an expanding universe works the same way, except instead of a walkway, it's space itself that's moving. Light emitted from a distant galaxy travels toward us at the speed of light, but while it's traveling, the space between us and that galaxy is expanding. The light has to cover more ground than it would in a static universe. By the time the light reaches us, the galaxy that emitted it is much farther away than it was when the light started its journey. A galaxy sitting at the edge of the observable universe today, about 46.5 billion light-years away, emitted the light we're seeing now when it was much closer. The light has been traveling for 13.8 billion years, but the galaxy has been receding the whole time. Space has been stretching, and now, 13.8 billion years later, the light finally reaches us, and the galaxy is 46.5 billion light-years away. That's why the radius of the observable universe is 46.5 billion light-years instead of 13.8. Space expanded while the light was in transit. The observable universe is not a sphere of constant size. It's a bubble that's been inflating for nearly 14 billion years, and we're sitting in the middle watching light arrive from farther and farther away as time goes on. But here's the twist. The expansion is accelerating. Dark energy, the mysterious force we talked about earlier, is pushing space apart faster and faster. Galaxies that are far enough away are receding from us faster than the speed of light. Not because they're moving through space faster than light, which would violate relativity, but because the space between us and them is expanding faster than light can cross it. Those galaxies are beyond the cosmic horizon. Their light will never reach us. Not in a billion years, not in a trillion, never. The space between us is growing too fast. They are, in a very real sense, gone, removed from the observable universe, not by distance, but by the expansion of space itself, and it gets worse. The horizon is shrinking, not in the sense that the observable universe is getting smaller. It's still growing as light from farther away reaches us for the first time, but the future visibility horizon, the set of galaxies we will ever be able to see, is shrinking. Galaxies that are currently inside the observable universe are slowly drifting across the horizon and disappearing. In a few trillion years, an astronomer in a galaxy that used to be part of our local supercluster will look out into the night sky and see nothing. No distant galaxies, no cosmic web, no evidence that the universe contains anything beyond their own galaxy. All the other galaxies will have receded beyond the horizon. Their light will never catch up. The expansion of space will have erased them from view. We live in a special time. Not because the universe was built for us or because we're important. Special because we happen to exist during the narrow window when the universe is old enough that structure has formed, galaxies have ignited, and the cosmic web is visible, but young enough that distant galaxies haven't receded beyond the horizon yet. A few billion years earlier, and the universe was too hot and dense for stars to exist. A few trillion years later, and the universe will be too sparse and expanded for distant galaxies to be visible. We're in the middle, the Goldilocks era, the time when the universe is just right for beings like us to look up and see the full picture. So what's beyond the horizon? What exists in the parts of the universe we can't see and never will? The simplest answer is more of the same. More galaxies, more clusters, more filaments and voids, more cosmic webs stretching out in every direction, following the same rules, built from the same initial conditions, organized by the same forces. There's no reason to think the universe suddenly changes beyond the edge of what we can see. The laws of physics don't stop at the horizon. Gravity still works, stars still fuse hydrogen, galaxies still form and collide. The part we can't see is probably a lot like the part we can. But how much more? That's where things get uncomfortable. The observable universe is huge, 93 billion light-years across, hundreds of billions of galaxies, trillions of stars, more planets than we could ever count. And it might be a tiny fraction of the total. Some models suggest the full universe is much larger than the observable part. Maybe thousands of times larger, maybe millions. Maybe the observable universe is to the full universe what a single atom is to the Earth, a speck so small that calling it insignificant would be generous. And then there's the possibility that the universe is infinite, not just very large, infinite. No edge, no boundary, no center, just space extending forever in every direction, filled with galaxies and clusters and voids, repeating the same patterns over and over without end. An infinite universe is not a comforting thought. It doesn't just mean the universe is bigger than we can measure. It means the universe is bigger than the concept of measurement. There is no total, no sum. No way to ever say we've seen even a meaningful fraction of what's out there. The observable universe would be an infinitesimally small patch, a single point in an infinite expanse, and everything we've learned, every galaxy we've catalogued, every structure we've mapped, would apply only to that one point. Is the universe infinite? We don't know. The data is consistent with a flat universe, which in cosmological terms means a universe that extends infinitely in all directions. But the error bars are large enough that we can't rule out other shapes. The universe could be closed, meaning it curves back on itself like the surface of a sphere. Travel far enough in one direction, and you'd eventually return to your starting point. Or it could be open, meaning it curves the other way like a saddle and extends infinitely but with a different geometry. The cosmic microwave background gives us clues. The temperature fluctuations in the CMB are consistent with a flat universe to within about 1%. But 1% is enough room for uncertainty. We can't prove the universe is infinite. We can't prove it's not. And then there's inflation. Inflation is the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. A tiny patch of space, smaller than an atom, doubled in size over and over again in an incomprehensibly short time. In less than a trillionth of a trillionth of a trillionth of a second, that patch inflated to a size larger than the observable universe is today. Inflation explains a lot. It explains why the universe is so flat. It explains why the cosmic microwave background looks the same in every direction. It explains where the density fluctuations that seeded the cosmic web came from, and it's been tested. The predictions inflation makes about the patterns in the CMB match observations almost perfectly. But inflation has a consequence that nobody talks about in polite company. If inflation happened, and the evidence strongly suggests it did, then the observable universe is not just smaller than the full universe, it's vastly, incomprehensibly, almost insultingly smaller. The region that inflated to become the observable universe was one patch among countless others. Each patch inflated independently. Each patch became its own universe, its own bubble of space and time, causally disconnected from the others. The space between patches has been expanding so fast that light will never cross from one patch to another. Each patch is an island, a separate observable universe. And there are, according to the math, an unimaginably large number of them. Maybe infinite. This is where the multiverse enters the picture. Not the science fiction multiverse where every decision you make spawns a parallel universe. The cosmological multiverse, the idea that the Big Bang we observe, the event that started our universe, was just one bubble in a much larger inflating space. That larger space, sometimes called the multiverse or the meta-universe, contains countless bubbles. Each bubble is a universe. Each universe has its own space and time, its own galaxies and stars, and possibly its own laws of physics. Here's why that last part matters. The constants of nature, the numbers that govern how particles interact and how forces work, appear to be finely tuned for life. Change the strength of gravity by a tiny amount, and stars wouldn't form. Change the mass of the electron, and atoms wouldn't be stable. Change the strength of the strong nuclear force, and atomic nuclei wouldn't hold together. The list goes on. The universe we live in sits in a narrow range of parameters where chemistry is possible. Stars can ignite, planets can form, and life can arise. That fine-tuning has puzzled physicists for decades. Why are the constants what they are? Why do they allow life? The multiverse offers an answer. If there are countless universes, each with randomly assigned constants, then most of them would be lifeless. Stars wouldn't form, atoms wouldn't bond, chemistry wouldn't happen. But in a tiny fraction of those universes, the constants would happen to land in the narrow range that allows complexity. And in those universes, life could arise. We live in one of those universes not because it was designed for us, but because we couldn't exist in the others. It's a selection effect. The multiverse doesn't explain why the constants are what they are. It explains why we observe the constants we do. We're here because this universe allows us to be here. The lifeless universes have no one in them to ask the question. This is called the anthropic principle, and it's deeply unsatisfying to a lot of physicists because it replaces a specific answer with a probabilistic one. Instead of explaining why the constants have the values they do, It says there are so many universes that all possible values get tried somewhere, and we just happen to live in one that works. It's not a testable prediction. You can't visit another universe and check if the laws of physics are different. The multiverse, by definition, is beyond the reach of observation. Each bubble is causally disconnected from the others. Light doesn't cross the boundaries. Information doesn't leak through. If the multiverse exists, we will never see direct evidence of it, but indirect evidence might exist. Some versions of inflation predict that bubbles can collide. If two inflating regions bump into each other, the collision would leave a signature in the cosmic microwave background, a circular pattern of slightly hotter or colder spots. Astronomers have looked. So far, no convincing collision signatures have been found. That doesn't rule out the multiverse. It just means if the multiverse exists, our bubble hasn't collided with another one. Or if it has, the collision happened so long ago that the signature has been stretched and distorted by expansion into something we can't detect. There's another possibility. Maybe the multiverse doesn't exist. Maybe the observable universe is all there is. Maybe the constants of nature are what they are because that's the only way a universe can be. Maybe there's a deeper theory, something beyond the standard model of particle physics and general relativity that explains why the constants have the values they do. String theory, which attempts to unify all the forces of nature into a single framework, predicts a vast number of possible universes, sometimes called the string theory landscape. Each point in the landscape represents a different set of constants and laws. If string theory is correct, and that's a big if because we have no experimental evidence for it yet, then the multiverse might be a consequence of the theory, or it might not. String theorists themselves are split on the question. The uncomfortable truth is that we don't know. We might never know. The tools we use to explore the universe, telescopes and particle accelerators and gravitational wave detectors, all rely on information traveling from distant places to us. Light, gravity waves, particles. If the information can't reach us, we can't measure it. The multiverse is beyond that boundary. It's not just far away, it's unreachable by the laws of physics as we understand them. You can't build a telescope powerful enough to see into another universe. You can't design an experiment to test what the laws of physics are in a bubble that's causally disconnected from ours. The multiverse, if it exists, is forever out of reach. So what are we left with? We're left with the observable universe, 93 billion light-years across, hundreds of billions of galaxies, 13.8 billion years old, structured by gravity into a cosmic web of filaments and voids, expanding, accelerating, cooling, aging, slowly drifting toward a future where galaxies are isolated islands in an ever-growing sea of darkness. That's the universe we can measure. The universe we live in. The universe that gave rise to stars and planets and, on at least one planet, life. And here's the thing, it doesn't matter if the universe is infinite. It doesn't matter if the multiverse exists. It doesn't matter if there are countless other bubbles with different laws of physics and different outcomes. None of that changes the fact that you're here, on this planet, in this galaxy. In this universe, the one we can see and measure and explore, the scale of the cosmos doesn't diminish you, it contextualizes you. You are made of atoms forged in stars that died billions of years ago. Your body contains carbon, oxygen, nitrogen, calcium, iron. Every one of those atoms was built in the core of a star or in the explosion that ended its life. You are quite literally made of stardust. That's not a metaphor, that's chemistry. The atoms in your hand were once part of a cloud of gas drifting through space. Before that, they were inside a star. Before that, they were part of the primordial gas left over from the Big Bang. You are a temporary arrangement of matter that has been cycling through the universe for nearly 14 billion years. You are not separate from the cosmos. You are part of it. A brief, improbable, self-aware part, but part of it nonetheless. The scale we've climbed, from quarks to the cosmic web, spans about 45 orders of magnitude, 45 factors of 10. You sit roughly in the middle, closer to the size of a galaxy than to the size of a quark, but not by much. The structures above you are vast. The structures below you are incomprehensibly small. And you, perched in the middle, have the capacity to understand both. That's the miracle. Not that the universe is large. The universe doesn't care about size. The miracle is that a collection of atoms organized into neurons and synapses can look outward at the cosmic web and inward at the quantum foam and make sense of both. You are a pattern of matter capable of comprehending patterns of matter at scales far larger and far smaller than yourself. That ability, the ability to measure and map and model, is rare, maybe unique. We don't know if life exists elsewhere. We don't know if intelligence is common or a fluke, but we know it exists here, in you. And the fact that you can sit on a rock orbiting an average star in an unremarkable galaxy and understand how the universe works, that's not diminished by the scale of the cosmos. If anything, it's made more remarkable. Humility is the first lesson of scale. You are small. Your planet is small. Your galaxy is small. The observable universe, vast as it is, might be small compared to what lies beyond the horizon. Every step up the ladder has reinforced that message. But humility is not the only lesson. Wonder is the second. The universe is under no obligation to make sense. It could have been a formless chaos, a random scatter of particles with no structure and no pattern. Instead, it's organized. Galaxies cluster into webs, stars fuse hydrogen into heavier elements, planets form from the debris. Life arises and starts asking questions. The fact that the universe is comprehensible, that the laws of physics are consistent and the structures are mappable is not something we should take for granted. It's astonishing. And the fact that we've figured out as much as we have in the brief time we've been looking is even more so. The third lesson is that the quest is not over. We've mapped the cosmic web. We've measured the expansion rate. We've found the Higgs boson and photographed black holes and detected gravitational waves. But there are still questions. Big questions. What is dark matter? What is dark energy? Why do the constants of nature have the values they do? How did life begin? Are we alone? Does the multiverse exist? Is the universe infinite? We don't know. And not knowing is not a failure. It's an opportunity. Every answered question has led to 10 new ones. Every solved mystery has revealed a deeper layer of complexity. The universe is not running out of secrets. It's an endless source of puzzles, and we've barely scratched the surface. Cosmology is not just about the universe. It's about us, our place in it, our origin, our future. The atoms in your body came from stars. The stars came from gas clouds. The gas clouds came from the primordial plasma left over from the Big Bang. Trace the chain far enough, and you're left with the question of why there's a universe at all. Why is there something instead of nothing? That question might not have an answer, or it might have an answer we can't comprehend. But the fact that we can ask it, the fact that we've traced the chain from quarks to cosmic voids and stood at the edge of the observable universe looking outward, is a testament to what a species can do when it decides to look up and wonder. The scale of the universe does not make you insignificant. It makes your existence improbable, remarkable. A fluke of chemistry and evolution that resulted in a pattern of matter capable of understanding the cosmos it's part of. You are not at the center of the universe. There is no center. You are not the reason the universe exists. The universe doesn't need a reason, but you are here. You are capable of asking questions and finding answers. You can look at a galaxy cluster and understand the dark matter holding it together. You can look at the cosmic microwave background and see the seeds of structure planted in the first moments after the Big Bang. You can trace the history of the universe backward to a singularity and forward to an empty, dark, cold future trillions of years away. And you can choose what to do with that knowledge. You can let the scale overwhelm you. You can feel small and lost and insignificant in the face of 93 billion light-years of space and trillions of galaxies and the possibility of an infinite multiverse beyond the horizon. Or you can let it inspire you. You can recognize that the fact you exist at all in a universe this large and this old and this structured is extraordinary. You can look at the cosmic web and see not a cold, indifferent expanse, but a history, a story, a process that started with quantum fluctuations in the first fraction of a second after the Big Bang and ended, at least for now, with you sitting here trying to make sense of it all. The universe is not about you, but it includes you. You are part of the story. A small part, yes, a brief part, but a part nonetheless. And the fact that you're capable of understanding the story, of tracing the scales from the Planck length to the cosmic horizon, is not diminished by the size of the canvas. If anything, it's made more meaningful, because the universe, for all its scale and complexity, is not separate from you. You are made of it. You are shaped by it. You are a temporary arrangement of its matter, granted the improbable gift of awareness, standing at the edge of the observable and looking outward into the unknown. That's where the journey ends, not with answers but with perspective, not with certainty but with wonder. The ladder we've been climbing doesn't have a top. Every rung leads to another. Every scale opens onto a larger one. And at some point, you have to stop climbing and take stock of how far you've come. From quarks to atoms, atoms to cells, cells to bodies, bodies to planets, planets to stars, stars to galaxies, galaxies to clusters, clusters to superclusters, superclusters to the cosmic web, the web to the horizon, and beyond the horizon, the unknowable, the unreachable, the infinite or the merely vast. It doesn't matter which. Because the part we can see, the 93 billion light-years we've spent the last 6 chapters exploring, is enough. It's more than enough. It's a cosmos so large and so intricate that 1,000 lifetimes wouldn't be enough to explore it fully. But we're trying. And that's the point. The universe does not demand that we understand it. It does not ask to be measured or mapped or catalogued. It simply is. And we, against all odds, are here, looking up, asking questions, building telescopes and accelerators and detectors, climbing the ladder, measuring the scales, tracing the flows, mapping the web, trying, despite the vastness and the complexity and the profound limitations of our position inside the system, to understand the cosmos we're part of. That's the final lesson, not that we're small. We already knew that. The final lesson is that smallness is not a limitation, it's a vantage point. You are standing on a rock in space, looking out at 93 billion light-years of cosmos, and you can understand it. You can make sense of it. You can trace the history from the Big Bang to the present and project it forward into the far future. You can measure the invisible dark matter and the mysterious dark energy. You can map structures so large that light takes hundreds of millions of years to cross them. You can peer into the quantum realm and watch particles behave in ways that defy intuition, and you can hold all of it, the entire ladder from bottom to top, in your mind at once. That's not insignificance. That's the opposite. That's a small piece of the universe capable of comprehending the whole. And if the universe is infinite, If there are countless other bubbles and endless other scales beyond what we can see, then so be it. The part we can see is still here, still real, still ours to explore. And the fact that we've come this far, that we've climbed from the Planck length to the cosmic horizon in less than a century of serious effort, suggests that the journey is far from over. The universe is 93 billion light-years across, at least the part we can see. And somewhere in the middle of all that vastness, on a planet that's barely a speck, you exist, wondering, measuring, climbing, looking outward and inward and asking what it all means. The universe doesn't provide the answer, but it provides the question, and the question is enough. We started at the bottom, at a length so small that the concept of distance stops working, a place where particles don't have positions until something bothers to look. We climbed through atoms and molecules, cells and bodies, planets and stars. We crossed the gulf between solar systems, mapped the spiral arms of the Milky Way, traced the flows pulling galaxies toward the Great Attractor, and stood at the edge of the cosmic web, watching filaments of dark matter stretch across hundreds of millions of light-years. And then we hit the horizon, the place where light runs out of time and the universe continues without us. 45 orders of magnitude. That's the climb, from 10 to the power of -35 meters to 10 to the power of 26. From the Planck length to the observable universe, and you, the thing reading this sentence right now, sit almost exactly in the middle, not at the bottom, not at the top, halfway up the ladder, looking both ways, capable of understanding both. That's the part that should break your brain. Not the size of the universe. The universe doesn't care about size. The part that should unsettle you is that a temporary arrangement of atoms, assembled by chemistry and shaped by evolution, can comprehend the whole structure. You are a pattern, a standing wave in a quantum field, a brief coherent fluctuation in the distribution of matter, and somehow, against all probability, that pattern has become complex enough to look outward at the cosmic web and inward at the quantum foam and make sense of both. The universe is not about you. It never was, but it includes you. You are made of stars that died before the sun existed. You are standing on a fragment of exploded stellar cores. You are held together by forces that operate faster than light can cross an atom. You are part of the web, one thread among trillions, and the fact that this one thread can see the whole tapestry is not diminished by the scale of the weaving. If anything, it's the only thing that gives the tapestry